Welcome to APEC. It's March 14th, 2026, and I'm your moderator, Tim Ventura. First, I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. I am traveling, so I am working remotely and moderating the conference there. Let me apologize if there are any issues with sound or visual quality because of that. So I am super excited. We have some amazing presenters today. This year in general is absolutely amazing. But today, Jamie Childress is going to kick things off with space-time as a material, a paradigm-shifting look at the vacuum as an active medium with real testable physical properties. After that, Douglas Miller is going to drill down on ZPE field intensity, SED, the Miller framework. He's basically looking at stochastic electrodynamics, and a lot of amazing physical effects just fall out of that model that aren't present in traditional models. So he's focusing on that today. And then Daniel Davis also has a pre-recorded drill down on warp-assisted hypersonics, engineering the shock layer, which is talking about controlling plasmas in hypersonic vehicles and shock layer physics that could reduce hypersonic heating and blackout, as well as serve as kind of a test bed for more speculative space-time effects. So I am really excited to kick things off. Again, apologies for having things so casual. This is kind of the APEC tradition, I guess, but it's been a while since I've gone without a studio. So I'm going to bring Mr. Jamie Childress in. Jamie, welcome.
Tim, thank you very much for having me. I really appreciate being here.
Absolutely. Well, thank you for presenting. So, like, APEC folks may not be familiar with you. Your brother is an author. He has written many books that they have read, like Anti-Gravity Grid, I believe that was one of them, right? So, but then you are also working on a new book, and yours is more geared towards hard science, right?
Yes, but we're not going to talk about that here.
Okay. Well, let me bring up space-time as material then, and I would say, yeah, I will take myself out. I'll be here if you need me, but just introduce yourself and take it away, sir.
Okay. Well, thanks for launching me and setting this up, Tim. So when Tim and I talked about having me on his show, one thing that I had to try and figure out, which was what kind of stuff could I realistically talk about? And that's because I, spent 40 something years working for the Department of Defense and for Boeing as a researcher. So I'm a now retired Boeing Technical Fellow, and during that time, I spent most of my career developing advanced one-of-a-kind systems or vehicles, invariably involving research into advanced physics. And so as a consequence, I have to sort of worry about whether something that I say or reveal is either proprietary or classified or whatnot. So in coming up with this topic, it had to be pretty generic. So let's just march on and go on to get launched here. So this briefing really is not so much a technical briefing about the details of various space-time effects so much as just a way to think about space-time and how changing the way you think about space-time maybe changes the things that you think you can do with it. Right. And so given the APEC audience, I'm going to assume that everybody is very familiar with a lot of the aspects of space-time that maybe the average person is not. So bear with me if I mention things that you're very familiar with. So, we'll just start off with space-time. Just what is space-time? So space-time is the stuff between everything else. It's the stuff between the stars. It's the stuff between subatomic particles. And because subatomic particles are small, but atoms are very large compared to the size of the subatomic particles, you are almost entirely space-time. You're, so every object around you and you yourself is almost 99.99999 something percent space-time. So So in fact, pretty much everything ultimately is space-time. And so, but because this is a discussion about really how to think about space-time, not so much exactly what space-time is, before we talk about the science of space-time, let's take a little detour into science. And this is something that I'm very, very well aware of because, for 40 plus years, I was, a research engineer, which is effectively a scientist. And so one thing I learned in that time is that science is not essentially a pile of data or a pile of results, if you will, but science is really how you think about the data, or you think about a test, or you think about what might be going on. And and invariably, a lot of my own career was spent researching things where nobody knew the answer, right? There wasn't a cookbook answer, nobody knew. So two people could look at a pile of data and oftentimes come up with very, very different conclusions. In some cases, completely diametrically opposite conclusions, right? So, so kind of to illustrate that, we're going to perform a simple test, and I myself am an experiment guy and a test guy, not a theory guy. So as a consequence, we're going to run a little test, a little experiment. And so that experiment is on the next chart, you are going to see a grid of geometric shapes. And what I want you to do is count the number of hearts among those shapes. And I'm going to give you 7 seconds to do that. Okay, so if everybody's ready, and here we go. You got 7 seconds. Okay, time is up. So hopefully, most of you discovered that there were 5 hearts on the previous page. And so, the real test here was not to discover how quickly you could count to 5 by looking at the chart and finding that there was 5 hearts there. The real test here was for you to discover what you didn't see. And so I told you to look for hearts. And so, presumably you did that. But ask yourself the question, how many white pentagons were there? Because there was lots of different shapes. And how many black pentagons were there? And so to help you sort of do that, let's conduct a little quick visualization thing. So kind of close your eyes for just a second. I'll close my eyes too, and we'll think, okay, let's take a second and go, well, how many white pentagons were there? Imagine it in your mind. Okay. Now, hopefully you have a number in your mind of how many white pentagons there are. Unless that number is 0, you imagined those white pentagons, because there were no white pentagons. There were some black pentagons, and actually I myself am not certain how many black pentagons there were, but there was a handful of them. So what this experiment really shows is that more than likely, when I told you to look for white pentagons, even though they didn't exist, you imagined that they did exist. And you may have some vague notions to how many black pentagons there were, or how many stars there were, because there was other shapes in there. But you don't really have a very clear idea. You certainly have much less clear idea than you had for the hearts. And what this illustrates is that you find what you're looking for, and you tend to ignore the rest. And we like to imagine that science is not this way, that science is really, boom, yeah, we've got this, man. But having been a research scientist for 40-something years, I'm here to tell you that that's not true. That, you can look at a data set, and if you're not looking for something in particular, it's likely that you don't see it. And so looking for material properties in space-time really helps you find them. So, and that's a critical thing to know. And so, which leads us into yet another thing, really, which a lot of people that sort of are on the outside of science don't really realize, is that belief is critical in science. So whether you believe in something, you don't believe in something, that really determines a lot of what you do or think about in a science experiment. So, if you believe that space-time is nothing, then it's really pointless to try and do research into how to touch it, right? However, if you believe that touching space-time is possible, that pretty much changes everything. And one of the things that it changes is that if you believe in something, you'll spend research dollars chasing it. And right now, there's really almost no significant funding for the idea of touching space-time. I mean, we spend all kinds of money on all kinds of things, but we spend almost no money, certainly no major government funding, certainly, in figuring out how to touch space-time. And treating space-time as a material, that suddenly makes quantum space research mainstream. So, in the APEC and Tim's audience in general, very interested in quantum space propulsion research, right? And the thinking of it as a material suddenly changes how possible that is. And a number of years ago, I gave essentially an internal TED talk at Boeing to a bunch of Boeing vice presidents and whatnot. And that TED talk started off with me saying that developing something is rarely about what is possible. It is almost always about what people believe. And so that is very, very true. So, you don't spend time and effort to try and develop something unless you believe it. That's the bottom line. So this talk is really about, let's see if we can help people believe that space-time is a material, and then that may change their thinking. So, one of the reasons that space-time has been treated as nothing for a long time is that back in the 19th century, space was called the ether. And it was believed that these ether vacuum particles transmitted light, or photons. The concept of photons didn't really exist too much back then, but it transmitted light, essentially the same way that sound is transmitted particle to particle. So vacuum ether particles transmitted light just the same way air particles transmit sound. And then back in 1887, the famous Michelson-Morley interferometer test showed that this wasn't true. And so in that test, they had two perpendicular mirrored arrays that formed an interferometer, and the picture in the right here is an interferometer pattern. And if that pattern is circular, then that shows that the speed of light in both directions is the same. And the theory behind this test was that the ether wind, if these particles existed, then Earth's own rotational movement as well as movement around the sun would be detected in this interference pattern and would show a bias. But it didn't show a bias. It showed that it was the same in all directions. And so what that test did clearly show, and in fact, I remember when I was in physics class about 1 billion years ago in the late 1970s, that I did the Michelson-Morley interferometer test, and sure enough, there were no ether particles, and which convinced me that space-time was in fact nothingness. But what does the Michelson-Morley experiment really prove? And what it does prove is that these ether particles don't exist. There aren't particles that transmit photons, one to the other. And what it also shows is that space-time, even if we do think of it as a material, doesn't interact with photons. And that makes the speed of light constant in space-time. And why it makes the speed of light constant in space-time is because if photons are not interacting with space-time, then, of course, their speed of light would be constant in space-time because there's no interaction. And speed of light is key to being constant, is key to relativity. And so there's all these bits of data that say, well, yeah, space-time isn't anything, right? Ether is real. Speed of light shows that's quite true. And of course, Einstein is been proven to be true pretty much every direction that you look when you look at relativity. So so the physics treats the lack of the ether wind as proof that space-time is not a material. And that's not necessarily a crazy viewpoint, but it also doesn't jive with a lot of more recent facts. And so one of those which is interesting, how two things that look very much the same are treated very, very differently. So I'm going to assume that the people that dial into Tim are familiar with dark matter, but if you're not, dark matter is something that was discovered decades ago, which was shown to be effectively the thing that holds galaxies together. So our own spiral galaxy is held together to a large degree by dark matter and would actually fly apart if dark matter did not exist. Yet dark matter, according to the very word dark, says that we can't see it, right? So the physics community assumes that dark matter is some sort of matter, which makes it material. So material and matter, it's really two different words that mean the same thing. And so there's lots of theories as to what exactly this dark matter is, but nobody's really claiming that dark matter isn't matter, at least not in the wider physics community. And so it's assumed that this dark matter is a material. And we are currently spending, billions of dollars, running big science experiments, trying to figure out what this material is and trying to find it. And when you try and find something, you're actually trying to touch it, right? Because if you're, the way that you see something, if you will, is to measure it. And when you measure something, you have touched it. Either you touched it with photons or you touched it with some other way. You touched it somehow. In fact, all of the current investigations to try and find dark matter and figure out what dark matter is involve attempting to touch it in some way. And so it's very instructive to sort of look at, well, let's do a little comparison between dark matter and space-time. So dark matter, it doesn't interact with photons, and it communicates with ordinary matter via gravity. Well, that looks a whole lot like space-time. Space-time doesn't interact with photons. It communicates with ordinary matter via gravity, i.e. space-time warping. In Einstein's universe, space-time is the fabric of the universe. Yet, for whatever reason, the fabric of the universe is not treated as a material. It's treated as effectively nothingness. Yet, dark matter is treated as a material. So that kind of makes you like, well, that just doesn't seem fair. Okay, so one of the reasons that space-time continues to be treated as nothingness effectively is that quantum field theory allows for fields to be propagated in a medium and the mediums being nothing. So for example, photons can propagate in nothingness via electromagnetic fields, which is an electric field, which creates a magnetic field, which creates an electric field, which creates another magnetic field, and just keep adding that for forever. So in that view, space-time can be nothingness. And so in the case of a lot of physicists, they think of space-time as being nothing. But one of the problems is that nothingness view really ignores the fact that those fields themselves, so let's say electromagnetic fields or Higgs fields or weak force or strong force fields, those fields themselves are part of the space-time material, and we can touch those fields, right? And as an example, so if you can touch something, it has to be real, right? So a couple of examples of the things that we methods that we have used to touch the material of space-time is the Casimir effect, which I'll go into the Casimir effect a little bit later, but I'm going to assume that most people who watch Tim's show are familiar with the Casimir effect and virtual particles and string theory. So string theory is a theory of everything that includes as many as 11 dimensions, and which brings up essentially a major aspect of space-time, which is both string theory as well as the existence of virtual temporary particles and whatnot. That the most logical explanation for those is that there are other dimensions beyond our normal XYZ plus time 4D space-time. And so a material that's partially resident in other dimensions is still a material, right? So no one says that a material inherently has to only exist in our 4D space-time. So, depending on whether you view space-time as nothing or if you view it as a material, actually does change what you believe is possible, right? Because you can't reach out and touch or alter nothingness, but you can touch a material. And more importantly, for space propulsion and a lot of the things that the APEC crowd looks at, you can alter a material, right? So if you start thinking of space as a material and talking about space as a material, then suddenly that alters what you sort of inherently believe is a possibility. So let's kind of review, if you will, the basic material nature of space-time. So some basic material properties of spacetime is that it's a material, but unlike any material made of atoms. It's not made of atoms, it's clearly made of something else. Exactly what it's made of, I think that the jury's out on that. But one thing we do know with absolute certainty is that spacetime does not interact with photons, and that because it doesn't interact with photons, speed of light is constant in spacetime. Another thing we also know with certainty is that fields are residents of spacetime, and not just electromagnetic fields, but all the potential fields, Higgs fields, everything. They're all residents of spacetime endlessly. And one of those fields is gravity, and some of the examples of gravity interaction with spacetime is gravity waves. And one of the things we know about gravity waves is that they travel at the speed of light. And because we have gravity wave detectors like LIGO, and who have detected gravitational, major gravitational events in distant locations, the instant that you have a detector of some kind, so like LIGO, what the detector, the fact that it's capable of measuring gravity waves, what that tells you is that it's capable of reaching out and essentially touching spacetime. So that gravity wave detector is actually capable of touching spacetime because the act of measuring something, like measuring a gravity wave, is the act of touching it. And so LIGO effectively proves that gravity waves exist, and you can't have a wave in nothing, and LIGO proves that we can touch that thing because we can measure it. If you can measure it, you can touch it. And again, yet another fairly obvious thing is that according to Einstein, mass curves spacetime, and we know that to be true due to things like gravity lensing in black holes, and you can't curve nothing. So spacetime clearly can't be nothing, yet it's still treated by big physics as yes, essentially a something that is by and large nothing. So let's go over again, like a little bit more about what space-time material interactions look like. And so space-time is a material that's filled with fields. And space-time is filled endlessly with these fields. And so probably anybody who's been, a frequent visitor of APEC is well aware of zero-point energy. In fact, looks like we're going to have a briefing on zero-point energy here very shortly. And what zero-point energy essentially says is, well, okay, the space-time, even if you take a chunk of space-time and wall it off from everything else, and you don't shine a flashlight into it, it's completely dark, it's completely, has no electromagnetic fields, that we're actively putting in there. We're not doing anything, it's just completely quiet space. That even so, that space is endlessly filled with all of the possible fields. So all of the possible frequencies of electromagnetic radiation and weak force and strong force and Higgs forces and gravity itself. And so all of that amounts to an enormous amount of energy. So every square inch of space-time is filled with enormous amounts of energy. And so, some of the things that are inherently there are virtual particles. So virtual photons are essentially the temporary force mediator within quantum mechanics of effectively electromagnetism or other exchanges of fields, right? And another one that's they're always there, which is virtual particles or virtual electron-positron pairs, which are responsible for vacuum polarization. And so again, I'm going to assume that pretty much most people that watch this show are familiar with the Casimir effect, but if you're not, the Casimir effect is an effect which basically says, okay, the vacuum space is constantly filled with all kinds of fields that surround everything. But if I take two plates and I bring them closer and closer together, well, the fields that are surrounding those two plates, they come in all kinds of wavelengths. And if I bring these two plates close enough together, the closeness of those plates is such that it excludes some of the wavelengths between the plates, but all of the wavelengths on the outside are still there. And at some point, the force from all those wavelengths external to the plates actually brings those two plates together due to the radiation pressure from virtual photons pushing on the outside being greater than the radiation pressure from the photons on the inside. So that's the Casimir effect, and it's something that has been demonstrated, so we know that it's real. So the fact that we have the Casimir effect, we can measure that these virtual photons and that interaction is happening. Therefore, we have been able to touch space-time. So the Casimir effect proves beyond a shadow of a doubt that space-time is a material because we touched it via the Casimir effect. And the same is true for vacuum polarization. And vacuum polarization is where you have electron-positron pairs constantly popping into and out of existence from space-time, from some unknown zone of space-time. And those electron-positron pairs create a measurable effect called vacuum polarization on electrons, because they shield electrons from other electrons and from other various subatomic particles. And we know that they exist because they affect electrons. So they've got to exist. If they are affecting electrons, then we can touch them literally through electrons. So another example of sort of space-time material interaction is dark energy. And again, I'm going to assume that people on this call are aware of dark energy, but just in case you're not, dark energy is the thing that is causing the expansion of the universe to accelerate over time. And if you read the science material on dark energy creates negative pressure within space-time. Well, negative pressure is simply a word that means anti-gravity, only you don't have to say anti-gravity. So it's a practical matter. Dark energy is anti-gravity, but science hates the word anti-gravity, so they're sticking with negative pressure. Yet other other evidence that of other dimensions in space-time is entanglement. So entanglement, defeats the speed of light, is faster than the speed of light, is effectively instantaneous. And for entanglement to exist, almost all theories of entanglement involve other dimensions besides our normal four. So entanglement, evidence of other dimensions. String theory, String theory, again, a theory of how the universe operates, and it has as many as 11 dimensions. So string theory is based upon the idea that there is a lot of dimensions, not just four. Virtual particles popping into and out of these other dimensions. And the universe is expanding in what? What is outside the universe? So, those are certainly aspects of space-time material. And one of the things that's worth discussing here is the fact that dark energy and dark matter were accidentally discovered. So no one was searching for them, and that's especially instructive in the case of dark matter. So dark matter, nobody was searching for it, yet they looked at the data and they said, well, man, spiral galaxies would definitely fly apart if it wasn't for something, and we're going to call that something dark matter, and it clearly is a material, at least according to our current best guess. There's this material, it's called dark matter. Well, as we just discussed, dark matter and space-time look a whole lot alike. And clearly, if you really looked at the data, you would conclude that space-time is a material, yet dark matter is inherently treated as a material. And so all that we really have to do to make space-time a material is have big science suddenly discover, well, hey, if we look at all the data, space-time is clearly a material, so let's call it a material. And the act of calling it a material sort of changes the game. And so a topic that often comes up here in APEC is quantum space-time propulsion in one form or another. And it's oftentimes, discussed as if it were reactionless. And my personal take is that it's not reactionless, that what might appear to be reactionless in our conventional 4D space-time is probably not reactionless when you include all of the potential dimensions in space-time. So, if you essentially say, well, okay, yeah, I may not be able to understand what this reaction looks like in my 4D space-time, that doesn't mean it's actually reactionless in some higher dimensional space-time, 5D space-time or whatever it might be. And that's true whether your quantum space propulsion is, some approach that allows you to swim through space-time via reaction to virtual particles, or whether it's a gravity-like effect. I mean, effectively, it isn't reactionless. It's actually reacting, against some dimension that we don't normally see. And so this brings us, ultimately around to where this talk, what this talk is ultimately about, and that is you've got to sort of ask yourself, well, why does it matter whether we call space-time a material or we just pretend to continue to call it nothingness? And the answer to that is that what you call something actually does matter. And like a prime example of this, since it's we've got the 250th anniversary of the American Revolution, is back in 1776, with the Continental Army, was called the rebels by the British and patriots by the Americans. And the difference between whether you call them rebels or you call them patriots doesn't change the Continental Army one little tiny bit, right? The Continental Army is still exactly the same, regardless of what you call them. But funding flowed very differently. The British funded a whole bunch of people to defeat the Patriots, and the Americans funded, the Patriots themselves. So your thinking and your funding flow according to what you believe. And so kind of keep that in mind, so that really, ultimately, it's all about funding. And so, I'm encouraging the point of this is to encourage people to think and talk about space-time as a material, both in, your discussions and in literature in your mind. And if you do that, it changes no physics theories and it changes no experimental data sets. But what it may do is change what you conclude from a data set, right? Because you'd be like, okay, well, this is a material, and what does this data say about that material? And it also encourages you to believe that touching is possible, right? So, if you think something is a material, you inherently believe you can touch it. You may not know exactly how to touch it, but you believe it's possible. And so by treating space-time as a material in science discussions, it increases the research into direct interaction with space-time, right? Because if you believe something is a material, you are like, oh yeah, let's go touch that. And so that promotes things like gravity modification research. And it promotes things like research into quantum propulsion, whether that's gravitational or some other particle interaction that, of particles that inherently exist in spacetime. So treating spacetime as a material takes us to the stars because we can't get to the stars with rockets. We can only get there through quantum, interaction with spacetime in one form or another. So that pretty much brings us to the close. So go out and socialize that spacetime as a material, and that actually can have an impact on research. So there we are. So Tim, back to you. We'll just open this up to whatever whatever comes next.
Yeah, absolutely, Jamie. That is so awesome. Thank you so much. I'm really excited. I think it's a wonderful primer, right? It takes people through the overview of what space-time is, why it matters. And so it's good to kind of revisit a lot of those fundamentals because this is a really mixed, diverse community, and everybody's coming at it with different preconceived notions, different background information, all that stuff. So before anything else, let me bring the crew in. We've got a pretty full house here. I'll take down the slideshow. Guys, please put your hand together and give Mr. Jamie Childress an enormous applause. And Jamie, let me thank you again. So it is only 40 minutes past the hour. Do you guys want to talk? Do you want to run through questions? Anybody have questions?
Question.
Fire away.
Jamie, awesome presentation. You covered a lot of ground there. Unfortunately, I wasn't quite able to take your vision of what you're saying and consider any direct experiments that anybody might be able to run. So I was wondering if you were to consider an experiment that you would like to see the open source public community run to pursue any of these ideas, what would be a direction that you think would be worth pursuing?
Well, actually, especially since Drew is on, the sort of work that is going on, with not just Drew's Exodus, but also in terms of other research that's happening relative to, let's say, quantum plasma drift and things of that nature. That, at the end of the day, if you treat space-time as nothingness, then essentially you inherently have to bring everything with you, right? So if you have space-time propulsion, so in order to in order to go to the stars, right, you literally can't get there with rockets. There is no method to get there with rockets, right? So if you, on the other hand, whether it's through plasma drift or by grabbing some other aspect of space-time, and although in discussions about the sort of work that Drew's Exodus is doing, it's referred to sometimes as it's reactionless, but again, in my own view, that's very unlikely, right? I sort of look at something and say, well, that probably action reaction is probably one of the very, very few aspects of the universal operating principles that is truly sacred. The difference is that, let's say, in the case of the work that Drew is doing, so they're doing that with fields, right? And so because fields are endlessly resident in space-time, the fact that their device moves itself through space-time apparently reactionlessly doesn't mean there's not a reaction happening in space-time. right? I mean, I don't know, Drew. What's your take on that?
What would we be reacting against? I mean, I know we're stealing momentum from something, and Charlie thinks it's third order perturbation theory, QED, virtual photon pairs, and we're somehow stealing momentum from one of those. But what does that mean? I mean, are we pushing off of something?
Well,
Some other dimension?
Well, of course, yeah, reacting in some other dimension, of course, is a possibility. But let's say in the case of your devices, so you have an electromagnetic field. You have very, very specifically an electric field, right? And that electric field does not exist in isolation relative to the rest of the universe, right? So your electric field is itself a perturbation of the natural fields that exist in spacetime, as we know from zero-point energy, as well as from quantum field theory in general. So quantum field theory is the root behind all quantum mechanics, right? And quantum field theory basically says, well, okay, every square inch of the universe is filled with all the potential fields. Well, in your case, you are creating effectively a perturbation in all these existing fields. So the fact that it appears to be reactionless, in reality, again, it's a matter of viewpoint. It is inherently changing the inherent fields that are otherwise always there, right?
I have no idea.
Well, I mean, I would liken that to essentially saying, well, okay, let's say there's a weather system in some part of the United States or some part of the world, right? That's actually a pressure change in some air molecules, right? And is that wind that's created by that pressure change, is that in isolation and the rest of the world be damned? And the answer is no. The wind that's created by that pressure change is actually a result of the interaction in the entire atmosphere and the Earth itself, right?
So you're saying we're part of some sort of universal butterfly effect?
Well, I'm saying that the fact that you create force doesn't make it reactionless. I'm saying that just like wind comes from a change in pressure from one location to another in the atmosphere.
Okay, so if I generated a million newtons of force to the left,
right,
somewhere in the universe, maybe even distributed out over the whole universe, the universe moves a million newtons to the right?
Well, what I'm saying is that the fields that you create to create your force inherently displace fields that otherwise would be there.
Okay. Is there anything in there that tells me how to make more fields and make more thrust? Because if there is, I am totally open to listening.
Well, we'll have to discuss that offline.
Okay.
Okay.
Thanks, Jamie.
You bet.
So, hi, Jamie.
Cool.
Thank you for your presentation. It was a very good presentation, and I think especially the point about the Michelson-Morley experiment needs to be communicated more and more clearly, because even at the time, people like Lorentz or Fitzgerald, for example, they had contraction ideas and to explain away why the drift didn't show up in the experiment. So basically, my statement has been for years, the Michelson-Morley experiment ruled out a specific kind of static ether background, but didn't rule out any kind of dynamical ether background or other kind of stuff. But it was interpreted in that way by many people. And today in the discussion, this is very a strong narrative, which has no real ground and basic. So I think it's very good to talk about space-time as something, because something has properties, right? And this is exactly a very interesting question. What kind of properties does space-time have? Does it have a structure? Also, like, there could be extra dimensions, but even in the dimensions that exist, could there be stored potential that you can release somehow? For example, maybe that is what Drew is doing, right? So maybe there's stored potential in the dimensions which can be released in a asymmetrical way to have a propulsion direction or a momentum transfer. So yeah. So what other properties could there be? And like the question of Jared, basically like the main goal question: how can we design experiments to really understand what the properties are and how to touch them, right? How to change them.
Yeah, and I think that my own view is I'm not going to pretend to know what space-time is. I think that the notion that space-time is nothing is if you actually look at the data is literally laughable. But I mean, and really what it boils down to is, what are people willing to fund? Because at the end of the day, developing something, again, is rarely about what is possible. It's almost always about what you believe. And if you believe that that space-time is nothing, then you're not going to spend any effort to figure out how to do something with it, right? So, really at the end of the day, changing that viewpoint has influences funding, so I mean, in the case of the sort of work that Drew is doing, in the development of any kind of quantum space propulsion, really, space-time being treated as a material sort of changes the way that you think about it. It may or may not change your experiment. Right. I mean, just like, okay, declaring space-time as a material changes exactly zero experimental results. But
and then what are your thoughts, Jamie? Have you dug into metamaterials at all? That's kind of a more interesting, for me, like space-time itself is difficult to modify, right, directly, but it appears that these gravitational metamaterials, Dr. Jack Sarfati has been writing about them, but a lot of other people have kind of picked up the mantle and started exploring that idea. Is that something you've looked at all?
Well, I can't go into things that, let's say, we looked at Boeing. So
Okay.
we can go there. But I guess what I would say is that things that we know happen and that we know must exist, like virtual electron-positron pairs, for instance. So, we know that they're real because they precipitate a vacuum polarization. We know that that's real, right? And so if we know that something is real, then trying to figure out how to utilize that thing that we know is real to do something useful, that starts to look like, wow, okay, that's a matter of spending the resources and the time, and actually invariably going down lots of rabbit holes that end up being dead ends, right? So there'll always be rabbit holes that end up being dead ends. The question is, are you willing to just keep hunting rabbit holes until you find something? And if you believe that there's nothing there to find, then you won't do that. Okay.
Yeah, it's amazing. Good, guys, do you have any other questions? We have about 10 minutes. And if you're, Jamie, if you're all set, we could go to Doug early, or if you guys have more questions, that'd be cool. So
yeah,
okay.
let's switch to Doug if that works for you.
Yeah, no, Jamie, thank you so much. Thank you so much. I'm pleased as punch. It is wonderful to see you again after all these years. I want to do a podcast with you too, as I mentioned before. Like it's going to take me a little bit to get everything kind of organized, rebuilt, but that would be super exciting. So
okay.
If I could just tack in one last one, Jamie, if people wanted to read more of your stuff or find out more of your stuff, is there a good place that they should go to do that?
No.
Okay. APEC only. I love it.
You're still writing it, right? You're still writing the book?
Right. Yeah. Yeah. So that's that's a work in progress. So yeah, it's gonna be well. Yeah. The book is The Science of Interstellar Travel. So you know, it's just gonna take a little while.
Yeah. When it comes out, come back on and promo it and all that. So.
Right.
So let's do this, guys. Let's put our hands together one more time for Mr. Jamie Childress. Jamie, I'm pleased as punch to be able to have you on and to be able to showcase what you're working on when the book is ready. Definitely let us know. We'll get it out there. We'll get links out there.
All right. Well, Tim, thanks for having me.
Thank you. Okay, so now I'm going to take everybody out except Mr. Douglas Miller with another butt-kicking stochastic electrodynamics presentation, because that one that you did, that was awesome. It was massive drill down, incredible math and physics. And so you are back to present more.
I am back. Thank you so much, Tim, for having me back to be able to present to you and your audience again about this exciting field.
Yeah. So let me do this. Let me take myself out. I've already queued it up. You can do the back and forth buttons, and I'm here if you need me at all, sir.
Yep, I've got the slides ready to go here. I see the buttons, so I'm ready to go.
Perfect.
All right. Well, I'm honored to be back at APEC to present on this exciting subject. This is going to be dense, and I've got a lot of material to cover. So just buckle up, and here we go. I have some very exciting things to share with you today. More and more people are no longer content with the status quo of QED. There's a change in the wind, and we're watching this change happen right before our very eyes in real time. And I'm on slide 1, correct? Yes. We're here to perform a forensic autopsy on modern physics and a resurrection of mechanical engineering. For 100 years, humanity has been trapped in a mathematical hall of mirrors called QED, quantum electrodynamics. But today, we're going back to the foundational fracture of 1924 to show you how we missed the most powerful engine in the universe, the vacuum itself. We will show you how physics traded a real physical continuum for a series of mathematical ghosts. I start with the premise that all matter and energy are emergent properties of ZPE field density. What if we could change ZPE density locally? Now let's go back to the foundational fracture of 1924 to 1927. In 1911, Max Planck published his second theory. He didn't just suggest a vacuum had energy, he postulated a real physical zero-point energy that existed at absolute zero. But between 1924 and 1927, 4 consecutive papers effectively ghosted this vacuum energy. 1, in 1924, Louis de Broglie suggested particles could be waves, but he left the medium out of the equation. 2, in 1925, Born, Heisenberg, and Jordan developed matrix mechanics, the first form of QED. It wasn't about the mechanics of the vacuum. It was about the math of the measurement. Number 3, 1926, Erwin Schrödinger gave us the wave equation. He visualized the hydrogen atom as a wave system, but again, the ocean those waves moved through was ignored. And in 1927, Heisenberg's uncertainty principle was the final blow. It institutionalized the idea that because we couldn't measure the ZPF-specific jitter, we should treat the vacuum as a mathematical construct, a placeholder of probability rather than a physical plenum. For the rest of this presentation, when I say jitter, I mean the German word that I cannot pronounce. I'm not even going to try to do that again. Despite Planck's second paper in 1911, postulating a real ZPE, these 4 papers turned the course of physics away from the classical approach and toward what is known as QED. This approach treats the ZPE as a hypothetical and only useful as a mathematical construct. At this point, I'm going to put a pin in the historical prelude and come back to it in a few minutes. Right off the bat, I want to address some serious misconceptions about the ZPE that I noticed after my last APEC presentation back in October. What the ZPE is. It's homogeneous and isotropic sea of stochastically fluctuating waves of all wavelengths down to the Planck cutoff length. They're non-propagation waves similar to ocean waves, or you could even think of cymatics, where the ZPE waves are stochastic superpositions of modes like resonant vibrations on the plate of the vacuum. They are Lorentz invariants. There are many more short wavelengths than long ones due to its frequency cubed spectrum. Double the frequency, example 1 Hertz to 2 Hertz, energy density jumps 8x. At 4 Hertz, it jumps 64x, and at 8 Hertz, 512x, and so on. Lorentz invariance for the ZPE waves has 3 consequences. 1, it means the velocities through the ZPE cannot be detected. Second, it means that the ZPE is made up of many more short wavelengths than long ones. And third, because the enormous turbulence of the atomic and subatomic scales, particles get jittered by the impacting waves of the ZPE constantly, giving rise to their quantum uncertainty in their position and momentum. Planck's constant, h bar, is a measure of this quantum uncertainty, and this uncertainty is dependent on the strength of the ZPE. This is another reason why Planck's constant is a measure of the strength of the ZPE according to SED physics. Another intrinsic property of the ZPE are its associated particle-antiparticle pairs. In QED, they're called virtual particles because they only exist as a mathematical construct. The caveat to that is that the theory suggests that upon reaching the energy level of the Schwinger limit, these virtual particles suddenly become real. In SED physics, they are not virtual because they're always real in relationship to the frequency cubed spectrum of the ZPE. Because ZPE waves are of all wavelengths moving in all directions simultaneously, dipoles of these waves will interfere constructively, temporarily forming very real particle-antiparticle pairs. In any instant, there are more than 10 to the 63rd such particle pairs in any cubic meter of space. This has several implications. 1, because these particles are electrically charged, they control the electric properties of the vacuum known as permittivity. And because these charged particles also move, and a charge in motion, an electric current, always produces a circling magnetic field, they also control the magnetic field properties of the vacuum known as permeability. Because the strength of the ZPE, the number of ZPE waves per unit volume, controls the number of particle-antiparticle pairs in a given volume of space, any change in the strength of the ZPE changes the number of particle-antiparticle pairs per unit volume. Now think about that. You think that might have anything to do with the Biefeld-Brown effect or Ferris-Williams dynamic theory unifying gravity and electromagnetism? I think it might. 2, because for their very brief existence, the particle-antiparticle pairs are very real, just like all other particles, they too get jittered by the impacting ZPE waves. Pairs are jittered at the constant frequency. This creates secondary radiation. 3, they can and do absorb light. 4, pairs enhance CPF Lorentz drag on accelerating charges. Implication, inertia emerges as vacuum resistance. And 5, Barry-Setterfield suggests the secondary radiation of particle-antiparticle pairs being jittered polarizes the vacuum, meaning net attraction toward areas of more virtual particle pairs, large mass objects. And this is the mechanism of what we know as gravity and why it's so weak. What SED is or what SED and the ZP is not, rather. Even though SED physics has been around since the 1960s and made somewhat popular by Heischrud and Puthoff in the 80s and 90s, it still remains that QED is the mainstream physics. Because SED physics has continued to be marginalized in 2026, SED is not an idea familiar to many people. Whether people have heard of it or not, they've been left with an unclear understanding of what it is. Some people try to describe it as QED with a little 0-point energy mixed in. Even a basic understanding of these things that I've laid out would dissuade this incorrect understanding. The 4 papers of the 1920s that led to QED's physics all came about as an attempt to explain Planck's first paper without a real ZPE. It stands to reason then that one cannot simply mix a real ZPE into the physics that doesn't acknowledge it as a real entity in the first place. Also, it is not the classical ether. Modern critics often conflate the ZPE with the 19th century luminiferous ether. This was the concept of a fixed mechanical Newtonian medium for light propagation. The classical expectation was that an absolute velocity through the ether could be determined. If the ether behaved like a static solid, then as Earth moves through it, we should be able to detect an orbital wind, since Earth's orbital velocity is 30 kilometers a second. It should produce a large fringe shift. Going back to the Michelson-Morley experiment we just talked about. A fringe shift was observed, but it was far smaller than predicted, corresponding to roughly 8 kilometers a second rather than 30. Textbooks call the Michelson-Morley experiment a null result, but the raw data showed a persistent small shift. Mainstream science ignored this because it was within the margin of error. Barry Setterfield, in chapter 7 of his book, Cosmology and Zero-Point Energy, recognizes it as partial entrainment. Even though an absolute velocity through the ether was not proven, the small fringe shift did prove something. Near large masses like Earth, the ZPF density is not uniform. The Earth entrains the ZPF. This has a refractive index connection. Setterfield notes that in the entrainment, this entrainment effectively changes the refractive index of space near the planets. The small 8 kilometers a second shift measured by Michelson and Morley wasn't an error. It was a measurement of partial entrainment and revealed that the vacuum is not in an empty void, but a physical frequency cubed spectrum and Lorentz invariant whose density is locally coupled to Earth's gravitational potential. It was the first unintentional measurement of a ZPF gradient. Summing up, you should now be thoroughly equipped with a basic understanding that SED is not QED with a little ZPE mixed in, and nor is it the classical luminiferous ether either. Now, big news this week. Something else needs to be mentioned here. And it's so new, I don't even have a slide for it. It comes about because of the Eric W. Davis and Eric Weinstein debate. Weinstein used a term I've never heard of before, and Eric Davis didn't seem too familiar with it either, EED. So what is EED? Well, I did some research. There's a lot of confusion right now because EED is not a single universally accepted theory the way QED and SED are. In current discussions, EED usually means extended electrodynamics or sometimes emergent electrodynamics. Different groups use the acronym for slightly different frameworks. It came about more recently in the 1990s to 2000s, and the idea is that electromagnetism itself might emerge from deeper vacuum structures. Examples appear in condensed matter analog models and topological field theories. It's suddenly popping up because, one, there's a lot of interest in vacuum engineering, two, the UAP advanced propulsion discussions going on, and three, gauge theory debates. Even though SED and EED started differently, they both imply the same deeper concept. Vacuum behaves like a physical medium. I don't like the word medium. Let's use plenum. Because of recent experiments, including the dynamic Casimir experiments, metamaterials that can reshape electromagnetic vacuum modes, and nanoscale resonators, vacuum engineering is starting to feel less philosophical and more practical. More physicists are becoming comfortable with the idea that physical constants and forces may emerge from interactions with vacuum fields. Fix the screen there. Both SED and emergent electrodynamics ultimately point toward a similar physical picture. The vacuum behaves like an electromagnetic ground state medium. Particles, inertia, and fields emerge from interactions with that medium. The biggest physics debate quietly forming right now is not QED versus SED versus EED. It's whether the vacuum behaves more like a quantum field or like a condensed matter medium or quantum fluid. Interestingly, this ties directly into another recent mic drop moment this week. Sonny White's paper, Emergent Quantization from a Dynamic Vacuum, published March 9th, 2026 in Physical Review Research. This paper explicitly assumes the vacuum behaves like a condensed matter medium or quantum fluid and shows that the quantum mechanics can emerge from it. That is to say, quantization is a resonance property of a dispersive medium. A lot going on this week. Now, let me get back to the historical prelude. Paul Dirac, 1902 to 1984. Dirac's work was central to the development of QED, the Dirac ghost in the ontological void. In 1928, Dirac formulated his equation merging quantum mechanics with special relativity. He predicted the positron, the first antiparticle. But to save his math from negative energy states, he had to invent the Dirac sea, an infinite ocean of electrons filling the vacuum. Dirac gave us the virtual particle pair. In QED, these pairs are ghosts, mathematical artifacts that pop in and out of nothingness. Because these ghosts create infinite energy results, physics invented renormalization, a fancy word for subtracting the infinity to make the numbers match reality. This created an ontological void, a physics that is incredibly predictive, but offers zero explanation for why the vacuum behaves as it does. Dirac's relativistic quantum mechanics and field quantization helped establish the dominant quantum field theoretic paradigm QED, which pushed classical alternatives like SED to the fringes. In short, Dirac's work was a cornerstone of the quantum revolution that elevated QED and marginalized the classic stochastic approaches like SED. At 0 Point Field Technologies, which is my company, we're paying off the Dirac debt and filling the ontological void with the science of the real ZPE with stochastic electrodynamics. The reality of the plenum. An SED is derived by key figures that we're about to explore. Virtual particle pairs are always real. They are the wave crest of the dipoles of the ZPEC. Matter does not pop out of nothing. It is a standing wave within the plenum. And once you realize a vacuum is a physical continuum, you realize you can apply hydrodynamics to it. More on this in a minute. Stochastic electrodynamics developed in the 1950s through the 70s by Timothy Boyer, Trevor W. Marshall, and De La Pena, and popularized later by Aish, Ruda, and Puthoff in the 80s and 90s, is a classical alternative that attempts to explain quantum effects through real 0 Point field fluctuations. Key figures and how their work challenges Dirac's framework and supports SED as a viable alternative. Timothy Boyer, 1941 to present. Boyer is the primary architect of modern SED. In a series of papers in 1968 to 1975, he demonstrated that classical electrodynamics plus a real isotropic Lorentz invariant 0 Point field reproduces several core quantum results: Casimir force, Lamb shift, blackbody spectrum, van der Waals forces, key point versus Dirac. Boyer showed that the 0 Point field's frequency cube spectrum provides the physical mechanism for the quantum fluctuations that Dirac's relativistic quantum mechanics treated as operator-valued fields requiring renormalization. Next, Trevor W. Marshall, 1947 to present. Marshall collaborated closely with Boyer. His work emphasized the stochastic nature of the ZPE and derived the Planck spectrum from classical SED, the origin of the Heisenberg uncertainty principle as arising from real ZPE fluctuations, not fundamental indeterminacy. Marshall's derivations directly counter Dirac's second quantization. The vacuum does not need creation annihilation operators, and real random EM waves suffice. Third, Louis de la Pena, 1931 to present, and Ana Maria Seto, 1946 to present. They developed a rigorous stochastic electrodynamics variant. Their books and papers, especially the quantum dice from 1996, show that quantum mechanics can be derived as the statistical mechanics of particles immersed in the real ZPE field, and a Schrodinger equation emerges from the Langevin equation with ZPE driving terms. They argue that Dirac's whole theory and negative energy solutions are unnecessary artifacts once the ZPE is treated as a real physical field. While I was putting together this presentation, I was curious if any of these people had any recent workout, and I found Ana Maria Seto's X account not very used at all, not many followers, not many posts. One of the most recent posts I found was from September of last year, and it had an article that is extremely relevant to this conversation. And so I'm going to read part of that article right now. It was posted in Physics World, September of 2025, called Quantum Foundations Toward a Coherent View of Physical Reality. 100 years after its birth, quantum mechanics remains one of the most powerful and successful theories in all of science. From quantum computing to precision sensors, its technological impact is undeniable, and one reason why 2025 is being celebrated as the International Year of Quantum Science and Technology. I agree with this. It's just that, in my opinion, SED could have done the same thing. Yet, as we celebrate these achievements, we should still reflect on what quantum mechanics reveals about the world itself. What, for example, does the formalism actually tell us about the nature of reality? Do quantum systems have definite properties before we measure them? Do our observations create reality or merely reveal it? These are not just abstract philosophical questions. Having a clear understanding of what quantum theory is all about is essential to its long-term coherence and its capacity to integrate with the rest of physics. Unfortunately, there is no scientific consensus on these issues, which continue to provoke debate in the research community. That uncertainty was underlined by a recent global survey of physicists about quantum foundational issues conducted by Nature 643-1157. It revealed a persistent tension between realist views, which seek an objective, visualizable account of quantum phenomenon, and epistemic views that regard the formalism as merely a tool for organizing our knowledge and predicting measurement outcomes. Only 5% of the 1,100 people who responded to the Nature survey expressed full confidence in the Copenhagen interpretation, which is still prevalent in textbooks and laboratories. Further divisions were revealed over whether the wave function is a physical entity, a mere calculation device, or a subjective reflection of belief. The lack of agreement on such a central feature underscores the theoretical fragility underlying quantum mechanics. More broadly, 75% of the respondents believed that quantum theory will eventually be replaced, at least partially, by a more complete framework. Encouragingly, 85% agree that attempts to interpret the theory in intuitive or physical terms are valuable. This willingness to explore alternatives reflects the intellectual vitality of the field, but also underscores the inadequacy of current approaches beyond interpretation. We believe that this interpretive proliferation stems from a deeper problem, which is that quantum mechanics lacks a well-defined physical foundation. It describes the statistical outcomes of measurements, but does not explain the mechanisms behind them. The concept of causality has been largely abandoned in favor of operational prescriptions, such that quantum theory works impressively in practice, but remains conceptually opaque. In our view, this is Ana Maria Seto and Louis de la Pena, the way forward is not to multiply interpretations or continue debating them, but to pursue a deeper physical understanding of quantum phenomenon. One promising path is stochastic electrodynamics, a classical theory augmented by a random electromagnetic background field. The real vacuum or zero-point field discovered by Max Planck as early as 1911. This framework restores causality and locality by explaining quantum behavior as the statistical response of particles to this omnipresent background field. Over the years, several researchers from different lines of thought have contributed to SED. Since our early days with Trevor Marshall, Timothy Boyer, and others, we've refined the theory to the point that it can now account for the emergence of features that are considered building blocks of quantum formalism, such as the basic commutator and Heisenberg inequalities. Particles acquire wave-like properties not by intrinsic duality, but as a consequence of their interaction with the vacuum field. Quantum fluctuations, interference patterns, and entanglement emerge from this interaction, without the need to resort to non-local influences or observer-dependent realities. The SED approach is not merely mechanical, but rather electrodynamic. Thank you, Ana Maria Seto and Louis de la Pena, for that amazing articulation from September of 2025. I mean, geez, he's 95 now, and she's 80, and still so passionate about the subject. Amazing. On to Louis de Broglie, 1892 to 1987. He was a French physicist who won the 1929 Nobel Prize for his 1924 doctoral thesis on the wave nature of matter. In 1927, he proposed a deterministic pilot wave interpretation, later revived by Bohm in 1952. Particles follow definite paths guided by real waves, classical-like reality that directly challenges Dirac's 1928 abstract operator formalism and probabilistic wave functions and second quantized fields, which produce the infinities that QED must renormalize away. This aligns perfectly with stochastic electrodynamics. The real ZPE fluctuations cause the jitter that maintains atomic orbits and produces the de Broglie wavelength. Heischrud-Puthoff, in their Physics Review A49 678-694 from 1994, derived the relation directly from the ZPF Lorentz drag on charges, treating waves as physical electromagnetic modes of the actual ZPE, not Dirac's mathematical abstractions. In the 1950s and 60s, de Broglie publicly regretted his earlier support for the Copenhagen interpretation and revived causal deterministic mechanisms or mechanics with hidden variables. His Lambark 1962 book, New Perspectives in Physics, states that physics took a wrong turn in the 1920s. Next, Anthony L. Peratt, 1940 to present. He's a plasma physicist, worked both at Livermore and Los Alamos. Peratt is not a core SED theorist, but provides complementary plasma cosmology support. His work includes large-scale electromagnetic simulations with Z-pinch and plasma filament experiments that reproduce galactic morphology without dark matter, and demonstrates that electromagnetic forces dominate gravity and cosmic plasmas, aligning with SED's emphasis on real EM fluctuations. Countering Dirac and establishing SED, Dirac's 1928 equation and second quantization were brilliant, but introduced virtual particles as mathematical constructs only, negative energies, and infinities requiring renormalization. Boyer, Marshall, and De La Pena collectively showed that most quantum effects, Dirac's framework explained, can be reproduced classically by a real fluctuating ZPE field obeying Maxwell's equations plus stochastic driving. No need for renormalization, creation operators, or virtual particles as ontological entities. ZPE itself provides the physical fluctuations. Perhaps plasma simulations reinforce that EM forces, including ZPE scale fluctuations, can explain large-scale structures without invoking dark matter or purely gravitational models. SED is not mainstream because QED's predictive success has kept it dominant. But these researchers demonstrate that SED is a viable, parsimonious alternative that avoids QED's mathematical scaffolding while reproducing its results. They also share a common agreement that the Copenhagen interpretation of quantum mechanics may be incorrect. In short, Dirac built the quantum edifice. Boyer, Marshall, De La Pena showed a classical foundation was possible all along, and Pratt extends the argument to cosmology. HRP expounded on these ideas in their seminal 1994 paper, Inertia as a Zero-Point Field, Lorentz Force, Physics Review A49. HRP's work is the bridge that made SED a serious alternative interpretation. It shows quantum mechanics emerges from classical electrodynamics plus a real ZPF without Dirac's operator formalisms or infinities. Their later papers further argue the points. Barry Setterfield expands on HRP's ideas in several important ways on his website, barrysetterfield.org, and in his writings, specifically Cosmology and the Zero-Point Energy. I'm going to skip to point number 2 here, time-varying ZPE density. Unlike HRP, who treat ZPF field as fixed, Setterfield argues that the ZPE density has increased over cosmic time. In the early universe, lower ZPE density meant inertial drag was weaker, a higher primordial speed of light, a lower Planck's constant, longer atomic lifetimes, and faster atomic processes. As ZPE density rose, Planck's constant increased, C decreased, stabilizing atoms and slowing atomic processes. Emergent constants from ZPE density, Setterfield explicitly links HRP's mechanism to his variable constant model, where Planck's constant is proportional to ZPF density, which measures the graininess of the plenum, and speed of light is proportional to 1 over the square root of ZPF density, and also where inertia and atomic stability emerge from this change in density. I'm going to skip this one. You can go back and read this one if you have the slides. In short, Setterfield builds on HRP by making the ZPF density time-dependent and cosmologically evolving, turning a static inertia mechanism into a driver of cosmic history and emergent constants. On to the Madelung equation synopsis. Erwin Madelung from 1881 to 1972 was a German physicist and published in 1927 the Madelung equations, which reformulate the time-dependent Schrödinger equation into hydrodynamic form. Here you see on the slide the 2 coupled equations, continuity equation and the momentum equation. And why these are crucial is they show quantum mechanics can be derived as the motion of a compressible quantum field with an extra quantum pressure term, Q. That produces non-classical effects, such as tunneling, interference, and uncertainty. They bridge wave mechanics and fluid dynamics, enabling quantum hydrodynamics. In the Miller framework, which we're about to talk about, and SED, they are essential for treating the ZPF as a real compressible quantum fluid, whose density gradients drive polarization, nonlinear saturation, Lorentz force asymmetries, and thrust scaling. Madelung's insight makes the ZPF a tangible, manipulable continuum rather than an abstract mathematical construct. In the SED view, the Madelung equations become extremely useful because they let us treat the real physical ZPF as a compressible quantum fluid whose density gradients produce the quantum potential Q classically. No need for wave function collapse, operators, or renormalization. One last person to talk about in the historical prelude before moving on to the Miller framework. Ferris Edward Williams. We conclude our historical prelude with Ferris Williams, a brilliant American physicist and former researcher at Los Alamos National Laboratory, best known for his dynamic theory in the 80s, a 5D unification model for space-time in one compactified dimension. His work aims to reconcile gravity with electromagnetism. It treats gravity, electromagnetism, and quantum effects as emergent from this higher dimensional geometry. Williams hypothesized that altering the 5th dimension could manipulate inertia and energy, potentially enabling warp-like drives or fusion enhancements. Yes, now that's the kind of exciting physics we're talking about. However, I state unequivocally that Barry Setterfield's emergent constants in cosmology offers a superior path over Ferris-Williams' 5D dynamic theory because it is more empirically grounded, physically intuitive, and consistent with observed data while avoiding the complexities of an extra dimension. Setterfield's model centers on the zero-point energy field's density as the driver of cosmic evolution. As ZPE density increases over time, Planck's constant rises, speed of light slows down, and other constants adjust proportionally with hc invariant to maintain atomic stability and the fine structure constant. This explains redshift anomalies, atomic decay rate changes, and cosmological fine-tuning through a real physical mechanism, the frequency cubed spectrum of ZPE waves surging the plenum's graininess. It's deeply harmonious with SED and HRP's work, where inertia emerges from Lorentz drag from this real field. And Setterfield's approach is testable, backed by historical data on C measurements and decay rates without invoking unobservable dimensions. In contrast, Williams' 5D dynamic theory, while innovative for propulsion, anti-gravity, superluminal effects, it's more speculative, relying on abstract higher dimensional math without direct empirical anchors, similar to string theory's challenges, and it lacks Setterfield's ZPE-centric focus, making it less intuitive for vacuum engineering and less consistent with SED's real field fluctuations. But, and this is a big but, it's not far off. If you substitute the compactified 5D dimension for the very real frequency cube spectrum of the ZPE and his mass density x to the fourth acting as a proxy for the ZPE, you basically have very nearly the same thing. Both versions embrace variable constants to resolve cosmological puzzles, example, fine-tuning and redshift, and counter QED's fixed vacuum and renormalizations. What it boils down to is that you don't need a fifth dimension, you just need an understanding of the frequency cube spectrum of the ZPE and its associated particle-antiparticle pairs, and what happens when you modulate ZPF density. Zero-point field technologies has made Setterfield's emergent constants in cosmology more engineering-oriented through the Miller framework, which codifies ZPE modulation into 6 pillars for practical applications, like our ZPF array, which is designed to be a first-of-its-kind, solid-state quantum hydrodynamic engine that pumps the local ZPE density gradients for quantum vacuum propulsion, directed Lorentz asymmetries, and vacuum-catalyzed aneutronic fusion applications. By integrating Setterfield's emergent constants with HRP's drag, we've transformed cosmological theory into metric engineering. This one, I'll let you read, and you can look back on that later in the slides. I'm going to skip ahead here. You can also go back and read this one. Now the bridge. Now we build the bridge to practical applications through the Miller framework, a paradigm for engineering the vacuum's emergent properties. We contrast QED's virtual constructs with SED's intrinsic particle-antiparticle pairs arising naturally from ZPE wave crests and dipoles, and address QED's extreme energy boundaries, such as the Schwinger limit, by introducing the recursive Miller saturation threshold as a more accessible onset mechanism for vacuum modulation. We will explore the 6 pillars of the Miller framework and demonstrate how SED enables tangible innovations in propulsion and fusion. We believe that our ZPF array will provide falsifiable predictions and tests that will position SED as the mainstream successor to QED by offering a unified, engineerable view of reality. From understanding the ZPF to engineering it, imagine the ZPF as an infinite ocean. Its waves crash stochastically, their superposition creating the subtle pressure gradients that jiggle particles and sustain atomic stability. But what if we could actively pump those waves, deliberately raising local ZPE density inside our cavities to engineer controlled pressure gradients and then direct that ocean like a symphony conductor to reshape reality? This is the essence of the Miller framework, developed at ZPF Technologies as an SED-based foundation for quantum metric engineering, drawing from Barry Setterfield's insights on emergent constants from ZPE density and HRP's model of physical Lorentz forces. The framework treats the vacuum as engineerable. This shift empowers innovations such as propellantless propulsion by creating directed ZPF asymmetries and vacuum-catalyzed aneutronic fusion by softening Coulomb barriers without extreme heat. Intrinsic particle-antiparticle pairs in SED. In QED, particle-antiparticle pairs are virtual mathematical placeholders In Feynman diagrams, they pop in and out as perturbative corrections require renormalization to cancel infinities and only become real at the extreme Schwinger limit. In SED, these pairs are intrinsic and physical. They emerge naturally from the real ZPE wave crest. Peaks create electrons, troughs create positrons, and driven by the frequency cube spectrum, they're always present as part of the plenum's stochastic jitter. No extreme threshold needed. Setterfield models show high frequency modes provide persistent pair fluctuations while preserving vacuum isotropy. This shift from mathematical ghosts to real vacuum excitations is what lets us engineer the plenum instead of fighting it. HRP and reinforcement. HRP showed that the real ZPF's Lorentz forces on charges produce the same jitter that mimics the de Broglie wavelength and uncertainty principle, but entirely as classical physics. In SED, each ZPE mode carries energy Planck's constant frequency over 2 with pair creation, threshold 2 mass sub E c squared for the electron positron. The spectral density formula you see here supplies more than enough high frequency modes for persistent pair flux at all scales, no Schwinger limit required. The frequency cube dependence is the mathematical smoking gun. Energy density explodes with frequency, ensuring continuous real pair creation for constructive ZPE dipoles. No external lasers needed. This is real parentology, the foundation of vacuum engineering. Replacing the Schwinger limit with a recursive Miller saturation threshold. In the world of standard quantum electrodynamics, the Schwinger limit is treated as a rigid breaking point for space. It is mathematically defined as the moment energy density becomes so extreme that you've packed an electron's worth of rest mass energy into a tiny Compton volume. Mainstream QED treats these pairs as virtual bookkeeping, mathematical fluctuations that are forbidden from doing real work until an external force promotes them to reality at the Schwinger limit. This is a distinction without a difference for an engineer. In the Miller framework, we stop hedging. We recognize that the spectral density means the vacuum is already at that energetic threshold intrinsically. We don't need to promote these pairs from a mathematical ghost state. We're simply modulating a real pair flux that is already performing the work of maintaining the vacuum's impedance. Now, practically speaking, the type of energy referred to by QED to reach the Schwinger limit is electromagnetic energy, requiring either intense lasers, example petawatt facilities like ELI or NIF, compressing pulses to 10 to the 18th volts per meter, or specialized setup of extreme plasma fusion conditions. In contrast to the brute force electromagnetic approach of QED, the Miller framework emulates Schwinger-like effects by modulating the local ZPF density itself. As we increase this density, literally thickening the vacuum with additional wave modes, the particle-antiparticle pairs of the ZPE intensify their relativistic jitter at the Compton frequency. This jitter, already moving at velocities near C, escalates until these pairs back-react non-linearly on the ZPF. They begin scattering and absorbing waves, saturating the vacuum's response like a fluid reaching its viscosity limit. This is where the big reveal happens. Because Planck's constant is a direct measure of ZPE density, as we pump the density, Planck's constant increases locally. This trigger starts a recursive loop. 1, it increases the electron rest mass. 2, it expands the Compton volume. Consequently, the very definition of the Schwinger limit, the energy density required to break the vacuum, increases along with power. As we pour density into a unit of volume, the volume expands its capacity to hold more graininess without fracture. This gives it a recursive nature. Unlike the hard Schwinger limit of QED, which suggests space-time will shatter like glass, reaching its fracture point, our vacuum softens like dough. It yields to our kneading, enabling sustained effects like softened fusion barriers and metric gradients. By leveraging coherent ZPF resonance rather than stochastic brute force electric fields, we emulate the nonlinear polarization of the Schwinger limit at approximately 7 orders of magnitude lower potential gradient or field strength. We aren't just hitting the vacuum, we're harmonizing with its fundamental frequency to rewrite the local metric. Instead of fighting the vacuum to create a pair, we're using high frequency actuation to harmonize with the Compton frequency already present in the background. Because we're pumping a resonance, the energy required to reach a nonlinear state is exponentially lower, similar to how a singer breaks a glass with a specific frequency rather than a sledgehammer. For these reasons, in the Miller framework, the electron rest mass over the Compton volume is renamed the recursive Miller saturation threshold. This recursive softening isn't just theory for us, it's the operational basis for the 6 pillars of the Miller framework. The Miller framework codifies SED's principles and its 6 pillars for vacuum engineering, positioning ZPF Technologies as a leader in metric modulation. Pillar 1, the Miller-Madelung transition. A resonance-induced shift of the ZPF from isotropic stochasticity to anisotropic polarization. We treat the vacuum not as empty space, but as a quantum fluid governed by Madelung hydrodynamics. The mechanism. The spectral density formula you see here establishes the ZPF as a high-pressure plenum. By concentrating these high-frequency modes, the array induces Madelung pressure gradients. The result? Inertial forces and radiation reactions are recast as viscous back reactions, allowing us to guide Bohmian flows into a state of coherent asymmetry. Talk about that on pillar 3. By inducing these pressure gradients, we change the metric compliance of the local vacuum. In plain English, we're making spacetime less rigid and more responsive to our pumping. We call this softening the metric, turning a stiff, unyielding void into a flexible, engineered vacuum. It's like a hydrofoil in a high-pressure stream. By modulating the density inside the cavities, we create a thick ZPF zone. The pressure difference between this engineered zone and the thinner ambient vacuum outside creates a suction effect, a net Lorentz force that pulls the lattice forward. We aren't throwing propellant out the back. We're engineering a pressure drop in the fabric of the plenum itself. Here you can see the formula. The formula in plain English says that the state of the vacuum is equal to the density of its energy multiplied by its phase or its internal rhythm. The continuity equation there tells us the vacuum follows the law of conservation of mass. It simply says the change in vacuum density over time plus the flow of that density must equal 0. In other words, the vacuum is a real fluid that can't be created or destroyed. It can only be thickened, thinned, concentrated, and skewed. When our array creates a surge, the fluid of space has to react. The momentum equation there, too, is the Navier-Stokes equivalent for the vacuum plenum, Newton's second law applied to a quantum fluid. It tells us that the fluid of space doesn't just sit there, it accelerates. Basically, the vacuum fluid accelerates under 2 influences, the classical potential and the quantum potential Q. Classical potential, V, is standard external forces. Quantum potential Q is engineered internal vacuum pressure. This is where it becomes revolutionary. Look at how we defined quantum potential. Notice that it scales with the square of the Planck constant. Because we're surging the local Planck constant, the metronome of the vacuum, we're not making a small adjustment due to the square dependence. We're leveraging an amplified pressure gradient. We're turning a whisper into a shock wave to drive the array. Implications: it enables directed vacuum stress for propulsion. Our device is designed to induce this transition via proprietary means. As you recall, earlier we mentioned Sonny White's paper, Emergent Quantization from a Dynamic Vacuum. This work provides the external bedrock for Pillar 1. White uses the exact same Madelung equations we do, treating the vacuum as a compressible quantum fluid whose density gradients produce physical structure. The shift is profound. White's paper effectively replaces the mathematical ghost of the vacuum of QED with a real dispersive medium. This means we can engineer the zero-point energy and create quantum wake thrust while fully respecting the conservation of momentum. Our framework rests on 3 pillars of White's validation. 1, quantization is emergent. Quantum effects result from a dispersive vacuum medium, not abstract operators. 2, fluid dynamics. We're applying standard Madelung hydrodynamics to that medium. 3, geometric engineering. Our asymmetric cavities provide the constitutive profiles required to trigger these emergent forces at scale. White's paper confirms what we are banking on for our ZPF array, The vacuum is a reactive, compressible, and highly engineerable plenum. Pillar 2 is the Miller constant, or the refractive index. In optics, the refractive index describes how light bends in glass or water. We're applying that same logic to the vacuum metric. By increasing the vacuum susceptibility, K sub m, we're effectively thickening the plenum. Think of it this way. It's much easier to row a boat in water than it is in air, because the water provides the necessary resistance to the oar. We're transforming the air of the vacuum into water, giving the array the traction required to couple with the plenum. We aren't looking for propellant, we're looking for impedance matching. Here's the formula. Mathematically, this traction is a direct result of the resonance with our cavities. As we pump the system, the local ZPF density surges, which proportionally reduces the effective speed of light inside the array. We aren't breaking the laws of physics, we're reauthoring the local environment in which those laws operate to maximize energy transfer. If you increase Planck's constant, speed of light has to decrease. The HRP connection, this leads to a radical application of HRP, definition of inertia. If inertia is fundamentally ZPF drag, then by modulating local vacuum density, we can modulate inertia itself. We aren't just sending a signal into the void, we're turning the vacuum into an active coupling medium. We're impedance matching the hardware to the quantum vacuum, allowing for high efficiency transfer of engineered momentum. So what? Well, it's the refractive index, K sub m, is our force multiplier. It determines our leverage over the plenum. By engineering a higher K sub m, we achieve metric softening, reducing the vacuum's inherent resistance to change. This is the exact mechanism required to soften the Coulomb barrier for fusion. We're making the vacuum more compliant, literally making it easier for matter to move and interact within our localized field. Pillar 3 is the Miller-Bohm propulsion, or the trajectories. Directed momentum extraction via Bohmian trajectories in a polarized ZPF using Lorentz force asymmetries. This is how we convert the thickened vacuum fluid into directed thrust. It's like a hydrofoil in a high pressure stream. The modulation creates the invisible rails that the array glides on. Inertial force ties directly to HRP framework. Acceleration distorts the ZPF spectrum, producing a back reaction, and the array's cavities asymmetries induce Lorentz imbalances, refracting stochastic flux into directed Bohmian paths. Implications: this unifies pillar 1 and pillar 2 into propellantless thrust. Through proprietary signal modulation, Bohmian trajectories are formed, effectively invisible rails within the vacuum fluid. This allows chaotic vacuum pressure to be rectified and directionally controlled. The core relation formula you see here, we return to the core physics of HRP. The effective inertial force is proportional to local vacuum density times acceleration. Inertia itself is vacuum drag. Formula is inertial force is proportional to minus ZPF density times acceleration. The minus sign is crucial. It tells us the vacuum is always pushing back against acceleration, exactly like viscous drag in a fluid. That opposing force is the drag we experience as inertia. Don't be confused though, the minus sign does not mean negative ZPF density in this case. Now usually this drag is symmetrical, but we have taken control of both variables. Through pillar 2, we engineer the density rho, and through our resonant frequency, we dictate acceleration alpha of the vacuum jitter. Our array's asymmetry then creates a Lorentz imbalance, refracting that chaotic energy into directed Bohmian trajectories. Think of the formula as the viscosity equation for the vacuum. Under ordinary conditions, the vacuum appears transparent. We move through it without noticing any resistance. But within the HRP framework, acceleration through the vacuum produces a reaction force proportional to ZPF density and alpha acceleration. That reaction manifests as a drag-like effect we interpret as inertia. The suction wake radiation reaction. What we're doing with the Miller framework is taking control of the ZPF density and alpha acceleration variables. By concentrating the ZPF density inside the cavities, we locally increase the effective viscosity of the vacuum. This enables the creation of a controlled gradient. Through our resonant frequency, we dictate the acceleration of the vacuum fluctuations. But the real magic is in the geometry. By using asymmetric cavities, we ensure that this acceleration isn't random. We're polarizing the alpha variable. We're forcing the vacuum to jitter in a way that creates a net pressure drop, a suction wake that pulls the lattice forward. We're controlling the density of the medium and the frequency of its reaction. By engineering this pressure gradient, we're rectifying the stochastic pressure in a single controllable direction. Visually, this would look like a vortex. Here's the array-specific expression. Looking at our array-specific expression here, you'll see that the force we generate is a direct function of the efficiency eta of our coupling and the square root of the energy inside the resonator. What this means for the hardware, eta ZPF is our proprietary coupling coefficient, how well our lattice grips the fluid, and the square root of gamma ZPF times E, the force scales with the energy density inside the cavity. The square root indicates a nonlinear resonant gain. And the local speed of light as we thicken the vacuum and the refractive index increases, speed of light drops, and the resulting force increases. This is our mechanical advantage. To wrap up pillar 3, 1, the formula tells us that any acceleration through the real ZPF produces a drag force proportional to local ZPF density. 2, in an isotropic undisturbed vacuum, this drag is perfectly symmetrical. It just resists motion in every direction equally. 3, our cavities plus resonance break that symmetry. They create a directional density gradient, higher ZPF density behind and lower ahead. And 4, that gradient turns the isotropic drag into a directed pressure field. In the Madelung hydrodynamic picture, any pressure field automatically guides the flow of the quantum fluid along defined paths. Those paths are the Bohmian trajectories, the invisible rails, visualized as a vortex. Pillar 4, the thrust scaling law. The definition, the quantum rocket equation. In traditional aerospace, we're governed by the rocket equation, which says your thrust is limited to how much stuff you can throw out the back. Consider this a quantum rocket equation, but there's one massive difference. Our fuel is the vacuum plenum itself. We aren't trying to carry it with us. We're using it as we go, much like an airfoil uses the atmosphere or a propeller uses the ocean. The formula, the power of omega cubed. Look at the core formula. As we established in pillar 1, the ZPF spectral density follows a frequency cube law. This is the secret to our scaling. As our signals are upconverted into higher frequency modes within the cavities, the energy density does not merely increase, it surges. This feeds back into the Miller constant. Mathematically, this produces a scaling factor of k sub m to the power of 1.5. The recursive snowball, the nonlinear surge. This creates a quantum snowball effect. Because the thrust scales nonlinearly with the vacuum density and our array increases the density as it operates, we get a recursive amplification. In plain English, the harder the lattice engine works, the thicker the vacuum becomes, and the more thrust we see. It's a self-reinforcing loop where the vacuum actually becomes more responsive the more you drive it. The implication, approaching saturation. The implication for APEC and for the future of propulsion is profound. We aren't looking at linear gains. We're looking at a system where thrust accelerates non-linearly as we approach the saturation threshold of the vacuum. We have moved beyond nudging the vacuum. We have found the mathematical and engineering key to leveraging the plenum for high-efficiency propellantless bursts. This is how we move from the lab to the stars. Pillar 5. This one's a doozy. This is the Miller limit and the quantum packing fraction. Ladies and gentlemen, we're introducing a brand new metric to material science, the quantum packing fraction, P sub Q. Sorry, my voice. Think of our ZPF array as a cage for an electron. If you design that cage to be 100 times larger than the electron's ground state, you create a potential for expansion. For a century, physics has asked one desperate question: how do we make quantum effects happen at room temperature? The world answered with liquid nitrogen and $1 billion cryostats to expand the de Broglie wavelength. We propose a different way. It is not about freezing matter. It's about quantum packing. The technical definition. In classical material science, we characterize a lattice by how it arranges atoms, the atomic packing factor. But in the era of vacuum engineering, that metric is incomplete. Our ZPF array relies on the quantum packing fraction P sub Q. here you see the equation. On the screen, you see our mathematical trigger, the quantum packing fraction. We defined phi sub q as the dimensionless ratio of the electron wave packet spatial expansion, the effective de Broglie wavelength, relative to its confinement volume within the Wigner site cell. Mathematically, it is the cube root of our 100-to-1 volumetric asymmetry, which brings us to our critical design threshold of 4.64. In the equation, you have V sub wave packet equals the effective electron wave function volume, and V sub WS equals the Wigner site cell volume. The trigger, the 4.64 ZPF array specific Miller limit. By engineering a deliberate 100-to-1 volumetric asymmetry, we modify the quantum phase space accessible to the electronic wave function. When phi sub q is approximately equal to 4.64, the cube root of our 100-to-1 asymmetry, the effective de Broglie wavelength expands to the Wigner site's boundary. This enables intersite overlap, a Mott transition applied to hardware. Yes, a Mott transition applied to hardware. At this threshold, electronic states become delocalized across neighboring lattice sites, forming a delocalized Madelung wave cloud. This is macroscopic quantum coherence at room temperature. Note, 4.64 is not a universal number. The logic here is universal. Coherence occurs when the linear expansion saturates the lattice. 4.64 is the specific sovereign frequency of ZPF technologies array. We've engineered our 100-to-1 geometric asymmetry specifically to trigger the MQC transition at this precise threshold, allowing us to hydroplane on the quantum vacuum without fracturing the metric. We have three emergent hypotheses. At the 4.64 Miller limit, the entire cavity array behaves as a single coherent superfluid interface, triggering three world-changing effects. One, metric softening, modification of the vacuum boundaries conditions, and effective electromagnetic impedance analogous to phase transitions and superfluidity. The array ceases to fight the vacuum and begins to surf it. Two, Coulomb screening, enhanced screening potential due to delocalized charge density. Theorized facilitate lattice-based interaction and enhanced probability of lattice-mediated nuclear interactions, ambient temperature alpha spikes. And three, geometric coupling, geometry-driven intersite coupling, forcing electronic coherence analogous to Mott transition induced phases, serving as a room temperature function equivalent to Cooper pairing. The scientific pivot here, Sir Neville Mott won a Nobel Prize for proving that if you force electrons to become big enough, material properties change instantly. We've taken Mott's vision and turned it into hardware. We aren't fighting the vacuum with brute force. We're tuning matter into harmony with the real ZPF plenum itself. The aha moment here is this. One, geometric condensation. We use our 100-to-1 cavity geometry to condense the ZPF flux. And two, quantum synchronization. We hit the 4.64 Miller limit to synchronize with that condensate, achieving an inviscid superfluid state where the lattice and the plenum move in total harmony. Pillar 6, the recursive Miller saturation threshold, which we kind of already covered. Earlier, we discussed the theoretical foundation of the recursive Miller saturation threshold. Now let's look about the engineering payoff. In Pillar 5, the Miller limit is the boiling point. Pillar 6 is the steam engine. Once we reach 4.64, the vacuum ceases to be a rigid barrier and becomes an elastic medium. We aren't hitting a ceiling. We're opening a recursive doorway. Under the Setterfield and HRP frameworks, we enter a self-reinforcing feedback loop. The ZPF surge raises local Planck's constant, the graininess of the plenum. The expanded electron wave packets increase the vacuum's energy holding capacity, and the system suddenly accommodates higher densities without dielectric fracture. It's a self-stabilizing ascent. The more the metric softens, the more resonance it can sustain. There's 3 stages of this transition. We can visualize this journey in 3 regimes. Stage 1, the resistive regime below 4.64. The vacuum is stiff. Every unit of momentum is earned against high impedance inertial drag. Stage 2, the transition threshold at 4.64, the knee of the curve. resistance begins to dissolve and the local refractive index, K sub m, accelerates. Stage 3, the superfluid regime above 4.64. We're now hydroplaning on our own wave wake. Motion generates a metric surge. The surge increases Planck's constant, and higher Planck's constant further masks the drag of the background plenum. The result is what we call the sovereign system, a self-contained metric soft bubble that is effectively decoupled from the standard inertial drag of the universe. At this moment, our array is no longer translating force against a vacuum. We're transducing the vacuum's own latent energy into directed flux. The vacuum has become the reaction mass, delivering the full refractive index and the 15 millinewtons baseline thrust that we have engineered. Yes, 15 millinewtons is what we're hoping to accomplish. Why hydrodynamics? Because the vacuum is not empty. In SED, it's a dense reactive plenum. When we modulate it at the scales of our array, collective behavior takes over, like a crowded concert floor that suddenly moves like a liquid. We're not pushing against the void, we're plumbing the plenum. Madelon gives us the fuel, Bohm gives us the rails, and Lorentz gives us the grip. Without all three, all you have is entropy. With all three, you have a solid state, quantum hydrodynamic engine. The vacuum is not literally a liquid, but behaves like one at high mode density. Metric suction is our shorthand for the asymmetric Lorentz back reaction and Madelon pressure gradients we create. Conclusion of the 6 pillars. By reaching the dimensionless 4.64 Miller limit and entering the recursive regime, we emulate the extreme nonlinear effects of the Schwinger limit, but at approximately 7 orders of magnitude lower potential gradient or field strength. Instead of needing petawatt lasers or high temperature plasmas, our array is designed to achieve the same kind of vacuum polarization and pair back reaction via the nonlinear multiplier to refractive index simply by resonating the real ZPF at room temperature. At that moment, the lattice should become a coherent Madelon wave cloud, a room temperature macroscopic Bose-Einstein condensate. The lattice walls will turn into a perfect superfluid interface with the plenum. The Coulomb barrier will become geometrically transparent, and we should see 8.7 MeV alpha spikes from the vacuum catalyzed anetronic fusion, all as byproducts of the same coherent state. Now, I had a little simulation worked on here, or worked up here. You can call it the fifth state of matter if you want. Maybe you don't like that. It's the Madelon wave cloud transition. In the metric soft regime, individual fermionic identity dissolves as electron wave packets bridge their Wagner-Seitz cells. This unified wave cloud acts as a single quantum fluid, enabling propellantless suction and zero resistance conduction. What you're seeing is the direct coupling between peak power input and the physical expansion of the de Broglie wavelength through the proxy of the ZPF energy density. So here you can see on the right, we got the one resisting lattice state, 1 being the relative Planck's constant, 3 wave packet dilation, 4.64 the Miller limit, 6 the superfluid regime. At 0 watts power, which is the classical state, you can see that the electrons are in their ground state confinement. The wave packet is a tiny dot in the center of a massive 100 unit Wagner-Seitz cell. The quantum packing fraction is near 0. At this stage, matter is cold, localized, and particulate. At 2 watts power, you have the inflationary phase. We start the actuation of the cavities and notice the packets beginning to breathe. At 2 watts, we've increased the local ZPF density enough to grow the electron by about 1.5x its original diameter. It's still a particle, but the fuzziness, the quantum uncertainty is increasing. At 5 watts, we're approaching the Miller limits. Expansion is accelerating. The electron is now 3 times its original size. It is starting to fill the walls of the atomic lattice. The impedance of the array is starting to jitter as we enter the three-threshold regime. At 8.6 watts, we reach the 4.64 Miller limit. The surge in local Planck constant stretches the electron's Compton volume until it hits the Miller limit, the point of geometric saturation. The linear expansion has reached the cube root of our 100-to-1 volumetric asymmetry, exactly 4.64. The so-called bird has filled its cage entirely. This is the knee of the curve where the physics begins to latch and thrust becomes nonlinear. At 10 watts, we have the phase transition and total overflow. The wave packets are no longer individual circles. They've merged into a single continuous Madelung wave cloud. The grid lines of the Wagner-Seitz cells have vanished. Individual atomic identity is gone. We've achieved macroscopic quantum coherence at room temperature. This is the recursive saturation threshold of pillar 6. What you're seeing in the sim is hardware phase change. It's the lattice opening up to the vacuum, but the real thrust comes from what the sim does not show, the back reaction of the vacuum plenum itself. As our cavities dynamically actuate, we're jittering the particle-antiparticle pairs of the ZPEC at Compton scales. We're effectively thickening the vacuum until it becomes a reactive superfluid along a very steep Madelung pressure gradient. This creates a high ZPF density zone behind the array and a low density depletion zone ahead of the array. The thrust is metric suction. The array lattice is drawn into the thinned vacuum. In the simulation, we model a growth rate of approximately 0.4 to 0.5 linear expansion units per watt. And to be clear, we're talking about peak resonant loading, not continuous thermal load. By utilizing sub-microsecond pulsing, we hope to achieve the energy density of the 4.64 Miller limit instantaneously. This allows us to exploit the staircase effect, where the vacuum's local refractive index remains elevated between pulses while maintaining a low average power load that preserves the structural integrity of the array. Crucially, this pulsing frequency allows for a metric flush, a periodic reset, where the local speed of light returns to C sub 0, preventing the slow light trap from bottlenecking heat within the lattice walls. We're effectively outrunning the thermal limit to capture the metric gain. Some final notes here. Please bear in mind HC invariance, a surge in Planck's constant, and the drop in C is invariant. The product HC remains constant. This explains why atoms don't fly apart as the metric softens and maintains the stability of the fine structure constant. I'd like to reiterate that propellantless suction means creating a metric pressure gradient. We're thickening the vacuum behind the wave packets, the dense backstop, while the front remains soft, effectively shielding the ray from inertial drag. One last thing here, connecting the engineering with cosmology. Primordial resonance emulating the day 4 pinch. To truly grasp why a mere 10 watts can trigger such a violent phase change in our array, we must look back to the history of the universe itself. According to Setterfield, our cosmos has already undergone the exact transition we are attempting to recreate in our array. In the earliest epoch, day 1 of the universe, the 0-point field density was remarkably low. The vacuum was thin. The speed of light was very high, almost instantaneous, and Planck's constant was low. Stable atomic matter could not yet form. Vast filaments of plasma expanded across the void without the stochastic jitter needed to pinch them into stars and galaxies. But on day 4, the ZPF density reached a critical threshold. As the vacuum thickened, Planck's constant surged, speed of light slowed, preserving HC invariance that keeps matter stable. And this increase in local vacuum resistance provided the physical pinch that compressed those filaments. As you know, plasma filaments are already unstable, into the first stable nuclear fires. Stars were born, galaxies were born, not through a change in temperature, but through a change in the constants of the metric itself. Our ZPF array is designed to perform a local day 4 emulation. We're not reaching for the absolute density of the primordial past. That would be impossible. We're reaching for the same geometric saturation point, the Miller limit, at phi sub q equals 4.64. By pumping the local ZPF density within our proprietary cavities, we force a local surge in Planck's constant. When we hit 10 watts, we're not just heating up the lattice. We're creating the exact pinch conditions where the Coulomb barrier becomes geometrically transparent and the vacuum itself begins to catalyze the reaction. So when we prototype this and we see those 8.7 MeV alpha spikes on our monitors, we are not seeing a nuclear byproduct. We're seeing the signature of a vacuum that has been reauthored. We're using 10 watts of resonance to awaken the same primordial forces that ignited the sun. This is not just propulsion. This is the liberation of energy from the plenum's breath. The Miller framework transforms SED into actionable metric engineering. ZPF Technologies is boldly leading this transition from QED to SED, from mathematical ghost to a real physical plenum. All that is possible remains to be accomplished. Jules Verne. For a century, QED confined the vacuum to abstract fluctuations and renormalization. SED restores it as a tangible, dynamic continuum ripe for modulation. By engineering local ZPF density gradients within our array, we will hope to achieve what once was unthinkable, that directed asymmetries in the Lorentz sieve for propellantless propulsion, vacuum catalyzed reactions that soften Coulomb barriers for clean aneutronic fusion, and tunable local metric effects that could redefine energy in transit, all in a flat Minkowski space without exotic matter or extra dimensions. This is no longer an academic debate. It's a new and existential engineering race to the future. And we stand as the vanguard, committed to rigorous R&D and ethical deployment. The vacuum is not an empty void. It's a vibrant sea awaiting resonance, and SED equips us to finally conduct its symphony. If you're interested in more information on ZPE, this book right here is my main primary source. This is Barry Setterfield's book. This man is 80 years old. He was offered 2 honorary PhDs for his life's work in this book. Talks all about the ZPE, as well as a lot of cool stuff about the implications of the ZPE back when it was lower in Earth's history, including things like gigantism in the fossil record. A lot of cool stuff in there. You can get it from their website, but they're 80 years old and they maintain it themselves. And when I tried to get a recent copy, it never shipped. And I called the number on the receipt, and it was his wife, Helen, that picked up the phone. And I said, "Hey, Helen, I've been corresponding with Barry over the years." She turns around, she says, "Hey, Barry, it's Doug Miller." And she said, "Well, he'll try to get it out to you soon. It'll probably be next week because he's got to put a battery in his car." So they're doing all this themselves, maintaining their website and sending out material. But they do say on their website that if you want a copy of this book for free, they can send it to you via email PDF instead. So thank you, Barry Setterfield, for all your work that I've been able to learn from and glean from and to share with this APEC audience. Thank you, Tim. That concludes my presentation.
Awesome. Doug, thank you, man. Thank you so much. Let me do this. I'm going to take the presentation down, and I'm going to bring, I'll bring all the guys in who are here. Everybody put your hands together. Enormous applause for Mr. Douglas Miller. I love what you're doing with SED. I absolutely love it. Thank you so much for presenting that for us.
Well, thank you, Tim. I appreciate the honor of being able to go through some things that I felt like were left a little bit vague last time around. There was some talk about what the ZPE was and SED was afterwards. And, it didn't sit right with me. So I wanted to clarify some of those things and then give a little bit of update on the framework that I'm working with our array. Obviously, I don't want to discuss any proprietary engineering designs of our array. That's all proprietary.
Well, I should ask if any of the guys here have any questions. The question I would have is, with the framework you're working, do you have any experimental results yet, or have you not made it to that?
Only simulated results, which really can't count for anything yet. A process like this can take 1 to 5 years to get to prototype. Obviously, money's involved, and obviously, in my point of view, a successful prototype would indeed prove stochastic electrodynamics physics.
And then you have a website, right? People can reach out to you.
I do 0-pointfieldtechnologies.com.
0-point Technologies. You know what? I'm going to try and put that up if I can. No.
Was that not it? Hold on.
Yeah, you might have to put that up in
it is. What is it? 0-pointfieldtechnologies.com. Let me type it in. Okay, I just uploaded it to the chat there.
Oh, okay. Yeah, I was doing different. Okay, so let me do this then. So yeah, sorry about the Doug. I want to do a share real quick, just so people can just so people can see. Open system settings. Yes, Google Chrome. Okay. Okay, and let me see. Then I will select a tab to share, and yes, hopefully that is working. Yep, there it is. Okay, that is the website. Awesome.
Yes, sir. And you can click on. So what you're seeing there is, the website's kind of designed a little bit for information and also to kind of attract investors too. And what you're seeing there is, you saw a couple of YouTube videos there. That's just, a couple of things you've done in your interviews there to show what's happening in the field so that investors know, hey, this is real, this is going on. This isn't something that is risky necessarily. And that's why those videos are there. And then you can click on the Miller framework. And that's something where I had a Gemini write like a little microsite and I just embedded it there. It's kind of cool.
Yeah, and so I'm dropping a link into the public chat also, and that way everybody can see it. They can check out the website. But I did want to put that up.
Thank you.
I'll take that one back down again. And did you guys have any questions for Doug?
I guess my question, Doug, great briefing, fascinating stuff.
Thanks, Jamie. I hope I didn't step on your toes. I know I kind of go hard against QED a little bit, and I'm not a fan of relativity, special or general. I think it was a construct of not having a real ZP in the first place. I think space is flat. I don't think you can curve it. So I didn't mean to step on your toes there.
No. You're not stepping on my toes. I started off by saying that I'm not a theory guy. I'm an experiment guy. So which leads me to my question, which is, okay, so you don't have any functional devices that you've built, but have you conducted some preliminary experiments to kind of convince yourself that this is grounded in reality?
I don't have any tangible physical experiments, no, but I think I am covered as far as that goes with kind of what I mentioned in the presentation with the kind of stuff Sonny White's working on, right? I mean, he kind of validates our pillar one right there. You know what I mean?
Well, I would let Sonny decide whether that's true or not. But
true.
Yeah, I wouldn't want to speak for Sonny.
But this is something that, no physical experiments, but I have been working on this framework for over a year. I work on it daily. Becoming an engineer was extremely hard. It's one thing to have a theory. It's another thing to put pen to paper and actually design something on paper that can then be transformed into a physical thing. So it's like I said, nothing physical experiment yet, but the process of becoming an engineer to be able to turn this into a physical product has been a year-long venture for me.
Yeah.
Sure.
Yeah. I got to ask the obvious question. How are you going to build this thing? I mean, is it an RF unit? Is it a frequency? Is it a radio? Is it a compressor?
Okay, well, it's on a wafer. It's a MEMS chip, so you're going to need a nanofabrication facility.
Okay. Try all that again in English.
A micro electromechanical systems device, a microchip. So we're going to need a nanofabrication facility to produce it.
Okay. So it's a physical little oscillator of some sort?
Yeah, it'll be about the size of your thumbnail.
And what, in theory, what field size will it be able to create? Will it be able to wrap itself in a field of some sort, or?
I think mainly it's going to have a higher pressure gradient within the cavities themselves. So the area right above the chip will have lower ZPE density there, and you're going to have a suction forward. And I currently, without being able to test this thing tangibly yet, I don't know if it'll have any bubble that encapsulates the entire chip or not. Which remains to be seen. I mean, obviously, we're talking about the cavity walls becoming a Madelung wave cloud with the plenum. Real implications yet to be seen, obviously.
None of that last sentence made any sense.
Well,
So I'm still trying to figure out. We build this thing, okay? It's this little bucket, whatever. This little thing. We build this little thing, and they turn it on, and it changes the space in front of it, and it just pulls itself forward. Is that the dream?
Space isn't empty. It's the ZPE density that we're changing.
Okay, whether it's empty or not, is this thing going to pull itself through this non-empty stuff that you call space?
It's going to be a suction effect. It's going to create. Okay, so when I first had this idea several years ago, I thought, well, what if we could create, if the physical plenum, if the ZPE is a physical plenum, and it's only accessible at nano scales, because at our scales, there is really no ZPE at our scales. It's very, very small scales. And the smaller you get, the more dense and powerful it is, all the way down to Planck cutoff lengths. So I thought, what if we could do something similar to a ship's propeller? What a propeller does is it creates a higher density on one side of the propeller and lower on the other, and that creates a thrust. And so I thought, well, what if we could make a nanoscale propeller?
It's not actually how a propeller works, but
pressure differential in the sea of ZPE, much like how a ship's propeller works in the ocean.
it's not how a propeller works in the ocean or in the air. But aside from that, so you're gonna grab a little chunk of space and push it out behind you or something?
yeah.
Again, we're going to create a pressure differential. A pressure differential. If you have a pressure differential, something's going to happen.
Yeah. So yeah, let's try and move on because we're kind of rehashing. We're going over the same ground again and again. But yeah, but again, Doug, that was awesome. I want to wrap things up so that we can go to Daniel's video. But guys, please put your hands together one more time for Mr. Douglas Miller. And I'll bring Dan back in. I think Dan is having internet issues. Dan, are you having internet issues?
Perpetually. I'm on a hot spot, so it's not the best today.
Okay. Well, guys, yeah. So I'm going to take everybody out except Dan, and we'll see how this thing wants to go today. Okay. And sorry about that. Okay. And then Dan, I have your video up, so I'm going to play this. So what I'll do is I will move us to the corner. Let me share that.
I'll probably end up dropping out.
Juggling here.
That seems what I've been doing the whole conversation. So just whatever you got to do.
Of warp-assisted hypersonics.
There we go.
I want to say that again. Warp-assisted hypersonics.
Oh, perfect.
So what this is, it's an idea I've been playing with for a few years now. And it's kind of emerging between the latest developments around warp drive research, converging with aspects of the hypersonic aerospace engineering that has been around for, I don't know, the last 20 years or so. And so there's in order to understand why this concept is at least worth exploring, is that you need to understand both the problems associated with warp drives as well as hypersonic plasma sheaths. So we're gonna probably start with the warp drive problem. So I don't want to recount previous lectures that I've given on here, but in essence, you have the Alcubierre warp drive. It's a solution to general relativity that was founded in 1994 by Dr. Michael Alcubierre, excuse me. And it's 2026 now, so it's a 32-year-old concept. and it has some problems associated with it normally. Two of which really are the only ones that we need to worry about for the purview of this talk. And so without going into too much detail on the specifics of the Alcubierre metric, this is something I've gone through before with you guys. The two main issues that we're going to be looking at are the negative energy, as well as the overall amount of that energy that's required. Traditionally, warp drives are said to require negative mass energy in the T mu nu, part of Einstein's equation, and that's problematic for all kinds of reasons. Without getting into debates on if Casimir effects are normal, or if the energy conditions of GR are valid to look, that's a different lecture. We'll just assume for this that negative energy densities are bad, right? And it was 2019. You had Dr. Chance Glenn, he's an electrical engineer, kind of was looking at the literature of the warp drive, right? And he decided to play with the math and the equations a little bit, and he figured out that if on the condition that your stress energy side has the medium that is doing warping of space-time, because remember in GR, you have space-time curvature tells matter and energy how to distribute, and the matter and energy distributions inform space-time curvature, and you end up with this kind of feedback loop, right? And so what he shows is that if in this stress energy you have a refractive index whose complex in the sense that its imaginary part is greater than the real part, when you plug that back into the equation, it actually pops the energy density out as a positive energy density instead of a negative energy density, right? And that's good, because we know, positive energy is a real thing. It's what all the matter is around us. We don't have to source exotic matter. We just have to find a right candidate medium. And so he started looking at materials that have such a property, and he initially started, I think it was like ethylene glycol or propylene glycol. It was one of those glycols, like antifreeze, right? Because it's a lossy dielectric, and it has these properties that you would need to at least be dealing with a positive stress energy if you're wanting to look at a warp drive. And he did some experiments where basically he made an RF resonant cavity that has this ethylene glycol, and then he would pump it with a particular RF frequency in order to put energy into it, so it would raise the energy density. And then he was shining an interferometer through it, through the center of it. It's almost like a washer. Excuse me. You can find the papers on that. They're pretty easy to find. But that particular experiment failed. They didn't pick up any noticeable effects. Turns out the energy densities he was playing with, you wouldn't expect to see anyways. Which is when he turned to doing spark gap tests, playing with atmospheric plasmas in a spark gap, and then shining an interferometer through them and pumping them with various RF frequencies and such, to see if he could get a predictive effect, because atmospheric plasmas also happen to have this complex permeativity with an imaginary part greater than the real part. Now, there's probably something to be said there about not just the complex permeativity, but also the rapidly forming energy densities. It's not just one or the other. It's both working in conjunction. But as I got thinking about that, I noticed among reading the literature that there's already an existing medium that has such a properties already around a vehicle, right? And that's the plasma sheath of a hypersonic platform. And so, what are these? What are these plasma sheaths in hypersonics? Traditionally, hypersonic is defined as Mach 5 or above. Now, it's not just an arbitrary number. It's really what is the slightly more accurate definition is when the bow shock of the object going through the medium starts to heat up the air in front of it in such a way where it starts to ionize and turn into a plasma. That is the very definition of a hypersonic. Okay. Turns out, when you look at the literature on these hypersonic plasma sheaths, right? So you have your aerodyne here, and then at the front of it, you'll get these plasma sheaths that form and then trail off behind the body, right? These are normally problematic for a few reasons. Now, like I said, this plasma forms around your body regardless. Traditionally, this starts to introduce some issues around hypersonics, reentry vehicles, and such that. And it is that very nature of it being a lossy complex dielectric, which leads to what's called a radio blackout or reentry blackout. So the plasmas here, if you try to send a radio signal through it, it interacts in the plasma in such a way where the plasma sort of absorbs the radio waves and they aren't able to connect through to the actual vehicle. And so then the vehicle has a hard time communicating with the outside environment, right? And so they started to play with ways where how can we manipulate this plasma, right? In order to make a little window right here so that you can get a signal of a certain frequency through, because you're changing the properties of the plasma in such a way there where it's now transparent to that particular frequency, right? Erase this here. See how do I want to word this? As people have started to play with, it's called hypersonic plasma sheath manipulation, to mitigate this blackout idea, people have started to realize that, or actually, it's not that people realize that you could manipulate just these plasmas by electromagnetic fields. You can manipulate any plasma with a properly tuned electromagnetic field. That's good. So they started applying that to this particular situation, and they start embedding electrodes within the skin around here to, and they've played with all kinds of crazy things using MHDs, using magnetic fields, using electrostatics, using electron injection into the plasma sheath to change the properties of it in such a way where they can get a signal through, right? And actually, communicate with the people or the sensors that are on board your aerodyne here. Okay, that's fine and dandy and all, but the hypersonics have another issue too. So here, we'll erase this, and you guys will have to bear with me here. It might seem like I'm jumping around a little bit, but this will come back full circle in a second here. So just bear with me. So let's say we have our hypersonic body here, right? We got our little dark star looking scramjet thing. As you have, we'll use green for the shockwave. as you approach larger and larger Mach speeds, so like at Mach 1, the shape of your shock wave might be about like, green's not showing up too well on the camera. Color you can see a little easier. We'll go back to blue. So as you have the shock wave here at lower Machs, it's at a very wide angle like this. But as you increase the Mach number and it starts to go faster and faster, very naturally, it starts to close in and get closer and closer to the body, or to your body as you go faster and faster, right? And so then once we start getting past the supersonic regime into the hypersonic regime, you start running into these scenarios where the shock wave will start hitting the body of your airframe in such a way where this becomes problematic, because it really messes with the aerodynamics of the thing you're trying to build. There's a lot of turbulence, there's a lot of forces going on, and once you are past a certain point here, once your shock wave starts hitting these your air surfaces to actually control and steer the airplane, it usually will end up destroying it, or something if it's not designed around it, or makes it so your steering isn't going to be as effective. So as you go faster and faster and faster, you have to make these control surfaces smaller and smaller and smaller so they don't interact with the shock wave, right? Well, that has the unfortunate side effect of, it's pretty natural. If you make your control surface smaller, you're gonna have less authority on your rudder when you try to turn, which means you're just never gonna be able to turn as fast. And now, mind you, this turns into a problem very, very quick, where if you can't make a sharp turn when you're going super fast, it might take hundreds of square miles just to make a 90-degree turn. Like the SR-71 was already a case of this. I think it was like roughly the state of Ohio to make a turn, just because it couldn't exceed a certain amount of G-force, right? Okay, that is a problem. The thing is, we're already playing with manipulating this hypersonic plasma sheath, right? Well, something interesting about plasmas is the speed of sound within your plasma is going to be different than the speed of sound within the unionized atmosphere. Okay. So now, if you can change where what the speed of sound is in that particular medium, you can actually get your bow shock to lift. I'll go to red this time. Sorry. So you can get it to, instead of being here really tight and running into everything, causing all kinds of problems, you can get that shock wave to exist within the plasma itself, in which case it lifts off the body just a little bit and it opens back up, okay? And starts to give you more room that you can play with again on your physical actuators. In doing so, it also reduces the amount of drag. You could almost think of it as like, and again, this is before the warp stuff. You can almost think of it as like greasing the air so you can slide through it better without making as prominent of a sonic boom. It's very important. But we can take it a few steps farther, right? So again, we're already playing with manipulating this plasma sheath with all kinds of electromagnetic fields and electrostatics and RF pumping and all this other stuff. Well, it turns out, if you can, we'll go to a top-down view. So if you got your hypersonic, that's a really bad picture. We'll just go with the regular aerodyne for now. If you can make it, and again, this would be wrapping around all sides of the vehicle. If you can make it so now just this side of the plasma is a little thicker and is a little bit more detached, or a little bit more detached or compressed, so it interacts with the incoming air a little bit differently on this side, it'll start to make a yaw. So you could start to pitch or turn, and you can turn the plasma itself into your aerodynamic control surface. This is an existing field already within the domain of hypersonic aerospace research, and it's called plasma actuation. And again, they have played with all kinds of different ways to actuate the plasma, because it turns out it's basically the same technology that they're already playing with to mitigate the blackout issue. And so if you can turn this plasma into an engineerable medium, so you can now get rid of your control surfaces, or at least make them so you don't have to put as much into your mechanical ones, and you can use the atmosphere and the bow shock and the plasma going around your aerodyne, so you can steer and also communicate with ground control, for example, or other craft. That right there is already very important for existing hypersonics going forward, and it's something that they're going to have to address, and they've been trying to address for the last 20 years. We've been making incremental improvements on this, right? Okay. Well, we already have a really high energy density at I'll go back to a 90 degree or a horizontal. You save your aerodyne here. In this plasma, as it's coming around the sheath and then it dissipates, it's already going to have a certain amount of stress energy associated with it, right? This is matter and energy. It's with a relatively high energy density. Actually, we're getting a little ahead. What do humans want to do when they have something that goes fast, right? They want to make it go faster. This is just hot rod mentality. I mean, you see it in pretty much any vehicle humans have ever created. There's somebody that comes along and says, oh, we can use this to make it turn harder. We can use this to make it go faster. How fast can we make it go? How hard can we make it accelerate? How hard can we make it turn? These are all very natural things. And so you start playing with this plasma actuation idea. You're saying, how effective can we make? Is it something that we can only use to assist the existing physical control surfaces? Or can we get rid of the control surfaces altogether and only use the plasma manipulation because it's just that good at it? We've been playing with it for a while. And eventually, as the human monkey brain of make the thing go faster, put more power to it goes on, well, remember, the nature of these plasmas here, they're already pretty high energy density, right? Okay. Well, we're going to start turning back a little bit into the warp drive stuff here. If you have a high energy density, there's going to be some sort of non-zero spatial curvature associated with it. Now, in a non-manipulated hypersonic plasma sheath, the level of gravitational distortion that you have going on within the plasma is going to be so low that it is never going to be detected by any current sensors. It's so low that it might as well be zero, but it's technically non-zero. That's why we call it non-zero. But remember what we said at the beginning of the talk about Dr. Chance Glenn and his work in relation to the warp drive stuff. If you have a medium with a rapidly building energy density as well as a complex permeativity with an imaginary part greater than a real part, that is a candidate medium to be pumped, enhanced, manipulated to have a high enough energy density where you do get enough of a gravitational well here at the nose of the ship where it might start tugging on the ship, right? And you will start to run into effects. Now, let's assume you're not even trying to make a warp drive. You're just trying to get this plasma actuation to be as good as possible. Eventually, they're probably going to start running into situations where, as they're turning on the actuators to try to make the plasma more intense, or stronger on one side or stronger on the other, to so they're working on steering and turning it, they're going to start running into situations where there's going to be a discrepancy between the ground sensors and the internal sensors, right? So we'll just use the case of a linear forward acceleration that's not turning at all, right? You might have a case where the rocket in this thing is performing a 1g forward acceleration. At least that's what it's supposed to be doing. But for whatever reason, the ground crew is externally observing about a 1.1g acceleration, while at the same time the sensors or the crew inside the aerodyne, inside of this plasma sheath, might be reading a 0.9g acceleration. That's a weird discrepancy. So what's going on here is, like what I said earlier, they might be accidentally or eventually going to accidentally run into these warp effects within this hypersonic plasma manipulation research. And if they don't quickly identify what's causing this, man, that could end really bad. At best case scenario, you get some really cool data to start correlating between, and they stumble into warp effects. Worst case scenario, the craft isn't designed to what's the word here? It isn't designed with that 0.2g difference in mind. Now, granted, they should be engineering in stronger tolerances, but they're called accidents for a reason. And you could run into some really bad situations where you might get the front of the thing to crack, and then all of a sudden we're at hypersonic speeds, and then that turns into a big catastrophic failure where it just turns into a giant fireball in the sky, and you lose however many millions of dollars or that that X team had put into this this project, right? So at minimum, there's a potential modeling discrepancy that they're going to run into. But what happens when they start taking that seriously and they start realizing that this can be a little warp drive? Now, I want to take a second here to distinguish between a warp drive and a warp bubble. All warp bubbles are warp drives, but not all warp drives are warp bubbles, right? Traditionally, the Alcubierre drive and most of the literature around warp drives are for a horizon-bound bubble for the most part. It's for doing superluminal velocities. That is not what this is. This ends up being like a really dirty, you could almost call it, warp assist on existing propulsion platforms. Okay, and so like you can end up with this. All right, so just for review here, you have your traditional York time expansion for an Alcubierre drive. This is what most people associate with a warp bubble. You have your interior where the craft is here, and then you're expanding space-time behind it and contracting it in front of it, and then that causes your forward acceleration, right? there have been people have talked about, it might not cause acceleration, it might be a boost field to where it just makes existing systems more efficient. That's a debate for a slightly different chat. This one's gonna kind of straddle the line between them. But what this warp assisted hypersonics aspect is going to be is really more of a, you're making a dip here and then it goes off, and it never goes into the negative energy. It doesn't expand space-time behind it. You're just contracting it a little bit at the front so it starts to tug on it. Now, mind you, if you know anything about general relativity, this is going to mean there's going to be a tidal force, because the difference between the amount of tug happening at the front of the ship and at the back of the ship is going to be different. Okay, this is one of the stresses that can lead to a catastrophic failure of the air system that we need to try to avoid at all costs. Okay, but if we can engineer the fuselage of the craft and the systems in it, well, to survive those tidal forces, well, if you're making a little gravitational well that's just tugging on the front of the ship here, well, this force here is mechanically connected to the rest of the ship, and it's going to start pulling the whole thing forward. And because the whole ship ends up nested here within this well, even the pilot himself might start feeling some of those G forces. And so you end up in this really cool situation where not only can you use the plasma sheath to aerodynamically steer your aerodyne here, but you're using this warp effect now to, let's see here, we'll erase this for a second. Let's say we got our little delta wing craft. If it's going and it's making a turn here, right, it's going to have G forces that are going to want to pull the person this direction, getting slammed up against the car as it rolls over type thing. And that's what every pilot has to train for. That's what fighter pilots have to train for. You see the videos of the centrifuge is them, practicing how to take 9 Gs for 30 seconds or crazy stuff like that. It's because they have to be able to physically survive these types of things. Okay. But now remember, as per GR and the equivalence principle, acceleration is the same thing as a gravitational pull. So as the regular inertia, as they go on, is going to want to take them to this, it's going to put a lot of G's accelerating one way as you're turning the other. If you start to have a warp field that's a little bit stronger on this side, because remember, this is the side that you're making you're making this side stronger, so it turns that way aerodynamically. Well, if you're also getting a gravitational well in here, it's also going to start to offset some of these lateral inertial G forces, and it's going to start to pull the pilot back towards the way they're turning. So they might be able to pull what looks like a 9G turn from an Eulerian external observer, but them as a co-moving observer, they might only feel 2 or 3 Gs, depending on how efficient and effective the setup is. This is a big deal, again, and this is why we're calling this field warp assisted hypersonics. You're assisting existing hypersonic platforms with a little warp boost, right? This is probably the easiest way to think about this. So this addresses the negative energy problem, as I already established, because this is this plasma is the right candidate medium that people like Dr. Glenn have identified the properties of which you would need to get a positive energy density in order to warp space-time to get a warp drive effect. That was his idea. I'm the one that's kind of expanded this into the realm of hypersonic plasmas, because I was able to, just reading the papers, your brain starts to make cross correlations, right? Okay, that's that solves one of the two issues that we said we'd talk about today. The second is around just the overall amount of energy required for something like a warp drive. The vast majority of the papers, when they're for their axioms or assumptions, they are using a 100 meter diameter or radius bubble going 10 times the speed of light, so 10c, roughly 4.2 or 4.3 light years to the nearest star system. And that's usually what people put in for their axioms when studying warp drives. Thing is, you have a few different mechanisms that do I have? Sorry. All right, where was I? All right, so the amount of energy required overall for we'll just use the case of a Kubi air warp bubble. Mainly, it goes by first the velocity squared, and then on top of that, the two other parameters you can adjust is the radius and the thickness, right? All right, mind you, also that was one of the other assumptions that most papers use for the thickness of a warp bubble. They put it at roughly about 100 times that of the Planck length, based off, I think it was a Fenning paper out of like 1999 or something like that. I'd have to double check the date on that, but you guys can go and find it. So obviously, these plasmas, the area of this plasma sheath is not going to be so thin that it's only 100 times the Planck length. That's absurdly small. It's going to be thicker, and when you make the thickness of the warp bubble thicker, great wordplay there. That is one of the things that will lower the energy density. If you make the overall radius or diameter smaller as well, that lowers the amount of overall energy. We wouldn't be playing with something that's 100 meters wide in this scenario. We'd be playing with something that's anywhere from the size of a model rocket up to eventually probably like something like the size of the space shuttle at the highest end if somebody actually built something like this. So those two things right there are already going to drastically lower the energy requirements. The other one is velocity. Remember, energies for a warp drive go by the velocity squared. And once you start getting into relativistic, especially the superluminal regimes, it really blows up the amount of required energy, as well as usually turns it into negative. But again, we've kind of already addressed that issue. So the thing is, this is not a superluminal or even a relativistic warp drive. This is squarely in the subluminal region by a lot. Remember, hypersonics are only 10 times the speed of sound, not 10 times the speed of light. So just in adjusting those parameters, as well as going by the velocities, in the velocity, not only have we addressed the negative energy issue that Glenn first broached on with the complex and dielectrics, you also are now broaching the overall energy requirement, because we're looking at a more attainable regime instead of you have to walk before you can run, right? And so that alone already really drives down the energy requirements by a lot. I mean, a lot. I don't have the math in front of me, but I've done some math and calculations in the past, and you can really get it lowered by quite a bit. Interestingly enough, and this is starting to get kind of a little bit deeper into hypersonic plasma territory. We'll really zoom into the front of the aerodyne here. Really, too, what's going on is the plasma sheath here is a very complex thing, and it's hard to model because you have to do a lot of people simplify it to a 7 species. Really, it's more like a minimum of 19 species. What do I mean by species? I mean all the different chemicals that are going to be reacting in this hypersonic within this plasma sheath, because you're heating up the atmosphere to thousands of degrees, right? Which then starts to cause high energy chemical reactions, which is part of what frees up a lot of the electrons to within here. I'm not going to list them all, but all different kinds of nitrogen, oxygen, and various forms, even just electrons. I'm not going to name like all, you know, like 19 plus species of chemical reactions that you have to account for. The important thing for the purview of this talk is that typically those tend to organize into layers within this plasma sheath. So you might have some of those reactions happening in a layer there, and then you'll have some happening in a layer there, and then you have some more happening in a layer there, so on and so forth, to where this now becomes a really complex layered sandwich of slightly different processes going on. You can almost think of a nesting of a dirty multi-layer thing that as they go and they trail out behind the craft, you know, then they recombine and they kind of homogenize more, and they're not as layered as they are right here at the boundary layer. And again, all of these are being compressed by the incoming electrons and atmosphere and et cetera, hitting on your actual surface here. Now, then once you start introducing electromagnetic fields, you can compress this even more to get an even higher energy density. And then again, remembering, because these plasmas are lossy dielectrics, we can then pump radio waves into them to increase their energy density even more. Okay, that's pretty good news, at least in the terms of warp drive, right? The thing I'd like to point out about this layered thing, though, is that if we look at the work of Dr. Travis Taylor, who has kind of made an expansion on the Vandenbroek, the multi-layer nested warp drive approach, he has figured out that looking at multi-layer warp effects like this also contribute to lowering the energy density. Again, you can go find his paper that was, I think, published last year. You can go out and find it. So where does this leave us going forward? We have a conceptual map right here of something that is plausible. So how do we go forward with this research program? What needs to happen to turn this into something more than an idea? The first things first is going to be likely confirming that you can get a detectable warp field out of an atmospheric plasma. The easiest way to do this is going to be probably by spark gap tests, which Dr. Chance Glenn has already been performing. So that would be a natural starting point. Once his spark gap tests are, you know, confirmed and independently validated, that would then be justification to then take it to the next level, which is starting to integrate more with existing hypersonic research institutions or programs or what have you, where you start to figure out how you can modify these existing plasma actuation systems in order to do the thing that we need, you know, make them stronger or whatever particular combination of secret sauce we need to come up with this. And then stick that into a hypersonic wind tunnel and then do testing there to get validation, to get more validation. And assuming that the wind tunnel testing goes, you know, all according to plan, then that would be justification to then take it a step farther into doing sounding rocket tests. So, you know, if, sounding rockets, if you're not familiar, you start with a rocket and then you put your equipment up, you know, in the nose, and you go and you launch it, and then you have your equipment do whatever tests that they're supposed to be doing. In this case, it would be, you know, running basically an open atmosphere version of the wind tunnel test, and then trying to collect the data off it. And if we can prove that there is a meaningful assist coming from these warp drive, or not these, from these plasma layers, that can't really be attributed to anything else other than, you know, making a little gravitational tidal force tug on the front of the ship. I mean, that right there is, it's a warp. At that point, you have experimental proof of a working warp drive. Granted, it's not a warp bubble. It's slow. It's dirty, but it's a proof of concept. The other way that you can do this is via modeling, because that's how a lot of existing hypersonics research is done. Because, you know, wind tunnel tests and sounding rockets are expensive. So a lot of times we will go and we will do simulations, computational analyses, and to kind of weed out some of the less plausible solutions and figure out, if this works in the simulation how we say it does, then this will be a good candidate to then port over into actual physical laboratory testing. Okay, so this kind of gets to the point where obviously doing a program like this is going to be very multidisciplinary. There's not going to be really, I don't think there's going to be any one person that's qualified to do all of this on their own. It's probably going to need to be a team of people working on this, right? So we're going to need a plasma physicist, a general relativist, and probably a hypersonic aerospace engineer at minimum. Those three things. I've already been working a little bit with Dr. Chancellin on this, but we've kind of hit a wall in our own intellectual capabilities, and we're at the point where we need some help to kind of further this program. First step would be going and we'll just draw our aerodyne again. You take your existing hypersonic plasma sheath, right? And we know roughly what the properties of this will be, right? We have lots of papers, lots of studies studying exactly this. So we can get approximations of the energy density and the temperature and the pressure and the electron density and the permeativity and all these other things. You can go figure out how to then plug those into the stress energy tensor of GR, see what shape it kicks out in the on the G mu side. What kind of shaping function would something like this kick out? Now, obviously, without being manipulated, it's not going to be strong enough where you would ever see it, but it gives us an idea of the shape. Now, once we have that shaping function, we can then go plug it back into GR and then find out, what kind of discrepancy do we need to make up for? How much energy are we going to have to figure out how to pump into this plasma where we can get the desired effect? Once we have that information, that's already a couple of research papers probably that's introducing a new warp metric that's designed more around hypersonic velocities instead of luminal ones, and then that would start informing engineers of what we need to do in order to make the thing happen, right? And so I see now we're at, roughly about the 45-minute mark. So this is actually probably an okay spot to end this particular talk. I think I'll leave like 15 minutes or so for any potential Q&A, or we can just go into the next speaker. That's entirely up to you, Tim. Yeah, any questions? We can go over to Q&A, and I hope to be hearing from some of you guys in the future. Thank you for your time.
Okay, sorry about that, guys. And why is it not? Oops. There we go. Okay, sorry about that. Looks like Joel's not here. Guys, please put your hands together. Enormous applause. Dan, thank you. Thank you so much. I'm really excited about the warp hypersonics. I'm excited about this idea of relativistic stuff mixing with hypersonic vehicles, right? It just seems like it's wide open territory.
Yeah, sorry about the audio quality there. I thought I boosted the audio and posted it, but apparently
that's okay. I'll do a breakout, and I'll put the breakout. I'll boost the audio quality for you. So, okay. Yeah. Did you guys have any questions for Dan?
Hey Dan, wouldn't it be easier to operate in a low pressure regime where it's real easy to make plasma? I mean, it's low temperature, low energy plasma,
I
but
mean,
it's still plasma.
I'm not going to argue that at all. If you guys can figure out a way to turn low temperature, low energy plasmas into a viable warp medium, I'm all for it. The thing with the hypersonic plasmas is they're a byproduct that we kind of have to figure out something to do with anyways when we're pushing through the atmosphere that fast. So, it's at least worth exploring, I think.
Yeah, but see, inside of a vacuum chamber, you can have a very controlled, low, low noise experience.
Mhm.
Because you can have all of the sensitive equipment that says whether you're producing thrust or not, and you could shape the plasma fairly easy by, I'm guessing, magnets or something. I'm not real good on plasma, but when I used to coat telescope mirrors, I used to do something called electrostatic cleaning, and it was just basically 15,000 volts off of a beer sign transformer, and it would fill my chamber because the chamber was at about 10 to the minus 4, 10 to the minus 5, and it would fill the chamber with this purple haze of death, and it was bizarre watching these little balls of plasma just just move around and through different metal structures and things, and it was very very easy to create that plasma. I don't know that it ever cleaned the telescope mirror, but it left me with a very good understanding of how easy it is to make plasma at 10 to the minus 4. So that might be an avenue that greatly reduces the price and puts the testing in the regime of guys like me, okay? Crazy people who have their own vacuum systems. It doesn't take that much to create a really good plasma at 10 to the minus 4, 10 to the minus 5. So just something to think about.
Well, and I think that's definitely valuable, especially as you start pushing higher and higher in altitudes. Like if you're trying to attach this to like an SSTO or something, assuming we've ever even got that far, the engineering. But no, yeah, I think that's definitely something that should be like modeled and explored more.
So Dan, I mean, I guess your own experience with dynamic testing. Have you done much of that?
No, I'm not an experimentalist. That's that's why I was saying in the talk. This is to me, it seems like it's going to have to be a pretty multidisciplinary program, and I'm at my current limits with it.
Well, so I actually spent my entire career, or just about my entire career, doing dynamic testing. So I started off working for the Department of Defense, doing ballistic testing and other high velocity impact testing and things of that nature. And one of the things, so I agree entirely with Drew, that in fact, generally I agree with Drew because he's also an experimentalist. But my thought on this is, having done many dynamic tests, is it's a very high probability in any dynamic test that the test itself will be screwed up, right? Because I mean, anything that goes down in time frames of milliseconds has all kinds of things that goes wrong with it, and also oftentimes the instrumentation gets screwed up. Right. So anytime that something is dynamic, the probability of it being screwed up is very, very high.
Well, and this is something that me and Jared were talking about before too. Is doing the thing and then actually getting testing the thing and getting good verifiable results are almost two entirely different problems, and it's past my scope at this point.
Exactly, and that's exactly why I agree completely with Drew that you're actually assuming that you want to test this out and see what happens, and then does that translate into some sort of work theory. You're infinitely better off to do it under controlled conditions and figure out, okay, yeah, the conditions may not be quite as strong as they might be in a dynamic condition, for instance, but that's actually more than compensated by the fact that you have a much more higher control over whatever's going on and a much better instrumentation possibility. So, so I think, so if I were you, if you were going to really pursue this, I would recommend, chasing, Drew's approach.
Okay. Yeah, and I understand there's a pretty high experimental barrier to testing this too, which is why I think a lot of there needs to be some more preliminary research done into the simulation and modeling side of it, just to see like, does the math even work out to even make it worth pursuing at the laboratory scale.
Right.
I had some. I didn't want to interrupt Charles. I think Charles was before me.
Okay, I'll quickly ask. If you had to guess, how would you create the negative energy densities needed for a warp bubble?
This wouldn't be a negative energy density. It would be a positive energy warp field, not necessarily a negative energy warp bubble.
Right, but if you had to guess, do you think there's any way you might be able to create those negative energies?
Oh boy. I mean, there's always the cop-out answer, maybe some kind of Casimir effect. But I mean, if I had a concrete answer for you, I'd be lying.
Yeah, Dan, I think you said before that it was the complex permittivity stuff was the cheater way to get away from having to use the negative energy densities. You can use positive energy densities through dynamically changing, right?
Yeah, and that's just like one of the cheats to get around the whole negative thing. I mean, even then, like there are ways to formulate warp drives within GR that don't have any negative energy requirements whatsoever, especially if you're operating in the subluminal capacity instead of the superluminal capacity. So like it's one of those cases where like I think some people aren't even asking, or they're not even starting with the right axioms yet, so to speak, and we have to figure out what those right axioms are.
So Dan, the part of your stuff that gets me really, really excited is how much overlap it seems like there is between this multi-layered squeezed plasma sheath stuff and UFO observables. For example, with UFOs, we see like RF interference in a broad spectrum, the kind that you would get if there was like a really loud arcing happening nearby, right? Like kind of this dynamic plasma. You have other stuff like the energy differences where the Nimitz Tic Tac going 80,000 feet drop in 0.8 seconds would require like terawatts of power, but observed power from UFOs tends to be in the, maybe megawatts or gigawatts range. So we have like a 1,000, 3-4 order of magnitude problem there. But if you had a 10,000 G maneuver of a craft and the occupants or the craft itself can only handle 1 G, then that's a warp factor of 10,000x. So by using your layered plasma sheath stuff, it seems like that's one way of achieving this warping within atmosphere, where these warp layers, these plasma layers, they're extending somewhat a distance away from the craft, and it's this gradient that you're getting of warping, such that as the craft is dynamically moving, these layers can kind of account for that and kind of drop these orders of magnitude problems down into the more feasible regime.
You could almost think of it as like it's a bad analogy, but like a magnetic cushion, so to speak. Take the analogy for what you will. Your mileage may vary, but there definitely could be something to that. That's why, like I was saying, I think really like a good place to start is just trying to start with modeling one of these hypersonic plasma sheaths that we know the parameters for, and then just model it in GR and see what it spits out. And that will give you at least a theoretic scaffolding to start building off of. Whether or not it can be extended in the ways that I think it can, that is entirely another thing. But at least with an existing warp drive literature, going from a single layer Alcubierre to a multi-layer Travis Taylor type warp drive in of itself is a way to really drive down the energy requirements. And like I mentioned as well, the velocities that we're playing with here, Mach 10 instead of 10 times the speed of light, already in itself is really driving down the energy requirements for a warp drive into potentially the megawatt scale, which is not planetary, which is what most of the literature says it takes. But that's what I was saying, is like a lot of these papers are starting from the wrong axioms.
Oh, couldn't you use atomic clocks also instead of a laser interferometry to see
Probably,
time dilation?
Yeah. That's
quite
something that's been discussed. Obviously, there's problems of itself that come with trying to synchronize atomic clocks versus play with trying to get good answers out of interferometer. That's what what we were saying earlier about how testing this idea is a whole engineering problem in itself. So it's one of those. It's going to be easier said than done, and this is not an easy program, but I don't think anything with a warp drive is going to be easy. So
You mentioned putting micro radio waves through the cavity, but I've heard Halpatoff saying they use terahertz, maybe waveguide.
Yeah, well, so the terahertz being used in the area of hypersonic plasmas is already a real thing, mostly explored in the blackout mitigation, because there's ways that you can manipulate the plasma so then it'll either become transparent or opaque to terahertz waves, and it turns out you can do some really cool stuff with terahertz and plasmas, but I still have to keep up with the literature review to make sure that's where I think it's going. You can probably find a lot of open source papers that will have some really cool information, even if you just if you look up some of the terms.
Okay, thank you.
Well, guys, thank you all. Do you guys want to go into open mic? Should we go in, or not open mic, but I mean, sorry, catch up on your projects. Sorry. Yeah, it's one of those days. I'm losing my voice too. But before we do that, guys, let's do one more applause for Dan. And I'm gonna put all of these up as breakout sessions on the Ultra Pult channel. I'm really excited about this, so I want people to visit that channel. Definitely subscribe if they haven't already. And then I'm also doing written stories on the website. So what I'm trying to do is get this stuff out on as many different channels as possible. And we have tons more coming. I mean, we've done hundreds of stories, and the Alt Propulsion channel has over 700 videos in one way or another, right? Many of those conference videos and presentations. So, we're just trying to get people engaged, get them interested, and get them exploring. So, yeah, who has lab updates for us? Jared has a lab update. Okay, take it away, sir.
I have a brief arts parts update. So recently, I always am trying to go down all the different rabbit trails possible to explain what's going on with arts parts. Well, one thing that I recently started going down was the bismuth layers. They're not actually bismuth, they are bismuth lead layers. And the ratio, when you look at the ORNL report, which, grain of salt, when you look at the ORNL report, it is a ratio of about 42% lead to bismuth. So almost 60-40 bismuth to lead, which is a very specific ratio that is used for very specific applications. That ratio tends to be used as a special kind of solder for soldering electronics, right? It turns out that bismuth by itself has a melt temp of around like 250 Celsius. But you add in that lead into it in that ratio, and it becomes a eutectic, which basically means that it's an easy, flow, low temp solder that now melts at about 125 Celsius. Okay, well, this sounds like, a nail in the coffin for human made. Maybe, maybe not. I don't know. But what it does potentially indicate is that it helps bring in the bounds on what kinds of operating principles may be going on in this potential UFO sample. That it can only get that hot before the stuff starts melting. So if there's some kind of electrical thing being used, which lead and bismuth do happen to have some kind of very specific applications. They're used for like a melt switch. Like if something gets too hot, it's supposed to melt, which will change the electrical characteristics, but it'll also help reflow the stuff. Kind of like in the old Xbox days, you get the red ring of death. You need to wrap a towel around the thing and like let it overheat to let the solder reflow. Kind of like that. If this thing gets too cracked and warped so that the layers aren't making good electrical contact, you can heat the thing up real quick and it'll reflow and it'll make a nice smooth electrical connection. So that combined with some other stuff going on in the magnesium itself seems like it could work pretty good as a heat sink, but it also has some other unique electrical properties that happen at specific frequencies that go away if that bismuth lead starts to melt. So it could be that this is a special kind of switch. The last thing I'll say is I think this kind of bismuth lead was used way back in the day for some nuclear cooling stuff, but that was like bulk level liquid stuff, not very thin 1 to 5 micron thick layer stuff. So the research continues, but I find it interesting that that ratio of bismuth and lead that is a very well-known 60-40 solder ratio for that stuff that hasn't been gone over yet by anybody else. So interesting stuff. That's my.
Okay, awesome.
Jared,
let me see, Drew.
rapid flyer stuff.
So it's just us left. I think Joel has his stuff turned off. Drew, do you have an update for us?
Yeah. Can I screen share?
Yeah, go for it. Do a screen share.
Screen share. Entire screen. Okay.
There we go. Okay, it's working.
Okay.
There we go.
Okay. This can take a little explaining as to what it is you're looking at. This is a sheet of polymer that has been metallized. In this case, it has aluminum on it. And this entire sheet of polymer is somewhere on the order of about 1 mil thick, 1,000th of an inch. And one of the experiments that I was messing around with was laser etching patterns into the polymer, just because, you know, I'm bored. And I'm discovering that lasers don't do what you think they're doing when you ask them to do something. For example, I said, at the lowest power setting possible, I said, you know, etch me a couple of lines. These are very small lines. These are only about 4 thousandths or 3 thousandths of an inch wide. Just from like here to here is only like 3 thousandths of an inch wide. And what it did was it blasted, you can see that it blasted away all of the metal on the surface. Then it burned away this material, and before it finished making this line, it burned a trough into this structure. This is what the bottom side of a laser cavity looks like, and it's been exaggerated quite a bit, but effectively, if this is a 1,000th of an inch thick material, this is about 4 10,000ths of an inch thick. So the laser pretty much evaporated away 40% of the surface thickness, of the volume thickness. And I tried a lot of different things to make that happen less. So it's a whole lot of experimentation. I'm just letting you know, if you think you can just go out and buy a laser and just magically do whatever it is you want to do to it, it'd really be useful if you had a $200,000 Keyence to play with, to tell you, that's a microscope, to tell you what it is you're actually doing versus what you think you're doing. So got a pretty rude surprise this weekend, or this last week, from all of this magic. And let me see what else there is in here. Yeah. Let's go back a few more. That's what it looks like in false color, and that's what it looks like just in black and white, and then that's again what it looks like in real color. So anyhow, that's pretty much what I've been doing. I've been trying to figure out why I'm having failures in the open air testing from stuff that works flawlessly in vacuum. And it turned out to be I was blasting away too much material, and the difference between these, basically, I'm basically creating a spark gap every time the field jumps into one of these little cavities. It tends to blow a hole right through the material. It's very, very depressing. So that's what I've been doing.
Awesome. Okay, well, let me take that down. Yeah, guys, I guess we'll cruise into open discussion if you guys have anything. Today's been kind of short, but we had good presentations. We've got good discussion stuff going on. So,
Question for Drew on what you just showed us. Any kind of performance increases that you're getting from that specific stuff?
Oh yeah, with the troughs, the little troughs, I probably get a 10x improvement in thrust output. I thought at first, I really did. I really thought at first it was the graphene that was being created, because I was when you burn hydrocarbons, of any kind, you leave behind carbon. That's just what happens when you burn hydrocarbons. So I started out. I may have mentioned a couple of weeks ago. I started out on a YouTube video where some guy was taking, I think it was Kapton tape, and he was put it down, and he was making graphene supercapacitors. Now, they were really, really low grade graphene supercapacitors, but they were indeed graphene, and it was indeed working. And so I did the same thing, and I generated carbon, and I thought, this must be graphene, and this is awesome. It turns out it was just carbon. I wasn't creating any graphene. And then when I ran the same test with all of the carbon washed out of the system, I was getting the same results as when I ran just the stuff with the carbon. So it had nothing to do with the carbon. It had everything to do with burning away more material. And more material burned away means you have a thinner base material. And thinner base materials work way better than thicker base materials when you're trying to create electrostatic pressure. I want to see the Graviflyer.
High up on a shelf, a little bit dusty.
Where's Mark?
He's around.
I haven't heard from him in weeks. I know he's stressed out about his family and stuff. Hopefully he'll take a break and come join us.
okay. I guess Joel is kind of, it's right now, this is 2026 chaos, right? It is. And Jared just moved. I just moved. I'm traveling. So, but overall things are going well. I've been working a lot on those AI stories on, let me see. Yeah, I'm not gonna. I won't show those here, but I'll show them on open mic. In terms of our visit, but I can tell you, in terms of our visitor traffic, we get about. Let me see. We're getting about 9,000 unique visitors to Alt Propulsion a month right now, and our YouTube channel is getting whatever it gets. I don't have the numbers in front of me. The website's getting around 9,000. And that's good, right? It's putting out stories. I mean, none of that's Tim stuff. That's all of that stuff is you guys. That's all your stories.
I got one more little update. Dr. Charles is going to do the Jesse Michaels podcast next week. So I don't know what the turnaround cycle is between record the podcast and whatever the podcast is going to be. It could be one day, it could be a month. I really don't know. But whatever it is, he's going to go record the thing next week.
Okay, well, that's wonderful. That's wonderful. Jesse, there was a post about that $50,000 prize, and it looked like it was in Jesse's Discord channel, and then someone reposted it in ours, and they were. I have no idea who it was, but it was somebody who didn't seem directly involved, who was upset with Jesse for not paying Mark or yourself. And my thought was, I mean, I could be mistaken, but when you guys were doing it, I think the goal was just to achieve the challenge, right? It wasn't a money grab. It was just
Yeah, we never participated in the money side of that challenge.
yeah.
But he wanted to see Jesse wanted to see something float around the desk. He wanted to see something flying around like a little Star Wars land speeder, just zooming around and doing all kinds of fun things. And he wanted to take it on the road with him. He wanted to physically take it and go home with it.
Okay.
And I told him that wasn't going to happen with any of my stuff. But we invited him down and invited him to look at the vacuum chamber and all of the coolness that happens in there. At the time we had a at the time we actually had a Unity engine or Unity thruster in the chamber, so he could have seen that. But he would have had to do the mental gymnastics of saying, okay, it's pulling that way at more than its own weight, which means that it can go that way in more than its own weight. But he wasn't particularly interested in any of that. And then Mark's thing was a perfect demonstration of at the higher pressures, that little spinning thing that he had in there was doing ion wind, because it was spinning in the direction that the ion wind was pushing it. And then as soon as the pressure kept dropping, it would eventually drop below the pressure at which ion wind could exist. And it switched into electrostatic pressure differential thrust. And it stopped spinning, let's say counterclockwise. And no, it stopped spinning clockwise, and it stopped, and then it started spinning counterclockwise. And that's the direction you'd expect from electrostatic pressure thrust. And I mean, that was a flawless demonstration of one type of thrust, which is an atmospheric phenomenon, into no thrust. There was just a kind of a balance between the two into electrostatic pressure thrust, which showed that you could make a physical object spin in a vacuum with this procedure, with these two very diverse things. And I can't think of a better explanation or description or presentation if you're trying to show somebody the difference between ion wind and electrostatic pressure. It did everything that you could possibly ask out of a demonstration. How that did not satisfy the challenge is beyond me. But again, I wasn't in it for the challenge coin. I was in it just because the guy turned up and he and Charlie struck up a friendship of some sort.
Oh, there you go.
That's awesome. And now he's going out there to do the recording thing, and that's awesome. That's what podcasts are all about: disseminating information to the people that want to listen to it.
Getting people involved, and that, like, for Jesse has done an amazing job for that. He has a massive audience. He got lots and lots of people excited about it. So I'm thankful for everything he's done there, and then we're just continuing to push stuff out there. And I'll tell you, with alt propulsion, I am really excited over the last year. I mean, everybody has been working their butt off, trying building new projects and getting the word out and this, that, and the other thing. But we're getting a lot of information out there, and it's getting people excited. And that's, for me, that's what gets me. That's why I'm doing this. So I just put up a big article on. I think I have to go to the website. I put up a couple big articles. You know what? I can share these real quick. Okay. Yeah, so I'll share the alt propulsion site. I think pretty much everybody has seen this now. This is it has my login stuff, so it's not going to look identical, but So one change that I made was, instead of having events on the top of the page and then having stories below, I just mixed them, at least for the time being. So the latest story and event is Bob Lazar's UFO. I just hit publish on this yesterday. This is based off of transcripts that I did analysis on for his two big 2-hour Coast to Coast AM interviews with Art Bell. That's like 4 hours of material. And then another 2.5 hours that he did with Joe Rogan. And so what I did was I took all of the technical info that he described, and I had it create a story for me. And I also did an appendix that goes into like the airframe, the reactor, the element 115, all of the stuff that's in kind of the classic Bob Lazar story. And like you guys would know as well as anyone, that was really controversial. So I'm not making claims about whether or not it's true. I'm just saying, hey, here's what Bob said. Use it as you will, you know. Then this one keeps making its round. Viktor Grabenikov's beetle wing levitation. I mean, Mark played with this. There's a bunch of beetle wings. A lot of.
I gotta tell you, Dr. Charles really likes that beetle wing thing.
Yeah,
he's got some deep connection to that concept.
So one thing, I'm gonna click on this link. I think this will work for you. Let me see. Yeah, there it is. So this link, and I can drop this into chat. I didn't know this was online. This is My World by Viktor Grabenikov. It's only chapter 5, and it was translated, but it has photos I've never seen before of him. This is on geomagnetics.org. Again, I'll drop this in. Has some of the samples he collected, some of the insect samples. Very interesting stuff. So for folks who are interested and want to learn more about beetle wings, this is what he actually wrote. This is his actual book. So I'm going to put this in here. And again, I do have a story on the Alt Propulsion site. And let me see. Then I had some others as well. This from ripples to rectifiers. That's graphene energy harvesters. There's the neutrino energy guys and Paul Thibodeau, who are working different angles of that and claiming results. This is John Brandenburg's GEM event. And then this is one, I thought this was interesting. Tom Vallone spent a long time doing research into zero bias diodes. Basically, he was trying to rectify vacuum energy the same way that the graphene energy harvester may. It's just a little bit different focus. So I did a big write-up on that. Okay, so that's what I got for APEC. So that's, you know, we have a lot of material. And then Mark is doing a presentation next week in New York City. Or no, sorry, April 3rd.
Yeah, Dr. Charles is going to be there. I think he's giving the keynote, or he's giving something. They talked him into going up there.
Okay, so let me see if, here it is. I will share this. Not that we promote other people's stuff on our channel, but like we totally do all the time. So, okay, this is what Mark sent me. Spacetime, Metric Engineering, and Quantum Vacuum Technologies. Friday, April 3rd. It is in New York City. I do not know exactly where. So Sonny White is going to be there with the Casimir stuff. Mark will be presenting on Falcon Space. They're going to have Manelli Durakshani. And Mark said, and let me pull up what he sent me.
Like I said, Dr. Charles Bueller will be there.
Bueller will be there also, yes. Right. So if people want to get involved with that, it's not letting, I will drop a link in, but it's deeptechweek.com. It's not even showing the registration stuff. So I'm going to stop sharing. I'll drop the deeptechweekend.com to chat.
That M31 Capital, it turns out that they're part of the JP Morgan Chase financial network of some sort, I think. There's a Morgan in there somewhere. Of all the different Morgans out there, I think it's Morgan Chase.
JP Morgan Chase. I think that's their.
Yeah, I think that's who that M31 is associated with.
Yeah.
Because the meeting's in one of those Morgan's offices. You know, in I don't know, somewhere in New York City, but in one of their offices, that's where the actual group get together is at. So.
Yeah. Oh, and there's Curtis. Let me see if Curtis has updates for us.
Hey there.
Hey, Curtis, do you have any updates, buddy?
Well, so I am working on getting some end caps made that I'm getting the design done for as you know, the Mega Drive had a brass side and aluminum plate, and the way we were mounting it had 4 mounts. So I'm redoing that, so it's like just basically hanging and reduces the chance of stick slip and stuff like that. So that's the main thing I've been working on, and I'm gonna be once that's done, I'm gonna get that machined. I'm looking at also replacing the brass side with the tungsten instead. So that's about it in terms of like the experimental side.
Awesome. Well, guys, I think that was everything that I had for today. You want to close things down early? Awesome. Okay. Well, let me do that. So yeah, this has been APEC for Saturday, March 14th. Today is Pi Day, 3.14. So yeah, March 14th, 2026. This has been an amazing presentation, and we have even more amazing stuff coming up. So thank you to everybody who joined us today, and I will have breakouts of these online in the near future.